Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. What is the universe? Silence, darkness. Before time began, there was nothing. No space to move in, no time to mark a before or after, no light, not even darkness, only a void beyond understanding. There was no where or when for anything to exist. It is nearly impossible to imagine a state of absolute nothingness, or perhaps a state where our familiar concepts mean nothing at all. And then, in an infinitesimal fraction of a moment, something changed. Out of the void, a point of infinite potential coalesced, a seed containing everything that would become the universe. Imagine everything and nothing, cradled together in a single point. No space around it, no time before it, only potential, waiting. Then, a moment that defies imagination. The point erupts. Not a burst into empty space, but an expansion of space itself. The fabric of reality unfurling. From smaller than an atom to cosmic proportions in a heartbeat, space-time inflates violently, doubling and redoubling in scale, faster than any light could ever travel. In absolute silence, the universe explodes into existence. But this explosion is more like the sudden stretching of a limitless fabric. Distances between any 2 points swell at a fantastic rate. In this initial breath of creation, chaos and order are one. All the energy that will ever exist is packed together and now rushing outward. The universe is born in that silent, searing instant. A foaming ocean of light and raw energy, brimming with possibilities. The newborn cosmos is a hot, glowing fog of energy. Space rushes outward faster than any light within it can catch, stretching and cooling as it grows. In that instant after creation, the temperature is so unimaginably high that matter as we know it cannot yet exist. There are not even atoms, only a shapeless fire. Forces that will later rule physics are entwined in a single unified superforce. But as the universe expands, this unity breaks. The forces separate into gravity, electromagnetism, and the strong and weak nuclear forces, each taking up its role. Amidst the searing glare, pure energy begins condensing into tiny particles. Like sparks freezing into snowflakes, ephemeral specks of matter flicker into being. Quarks, the small kernels of matter, pop out of the energy field and join in threes to become protons and neutrons. Electrons whirl into existence. These particles and their opposites, antimatter twins, appear in pairs, colliding and vanishing in flashes of light. It is a wild, churning state of being, an unimaginable ballet of particles. For an instant, a proton might spring forth, only to meet its mirror opposite and vanish in a flash. This dance of creation and destruction fills every tiny fraction of space with constant activity, like popping foam on the crest of a wave. A frantic balance of creation and annihilation reigns, matter and antimatter wiping each other out as soon as they form. Yet by a quirk of fate, a slight excess of matter survives this mutual destruction. Out of countless annihilations, only a tiny fraction of matter remains, without being cancelled out by antimatter. Those lonely survivors will eventually form all the galaxies, stars, and planets we know. Within the first fleeting minutes of its existence, the universe cools just enough for some of the protons and neutrons to stick together. They fuse and form the nuclei of the simplest elements. Hydrogen is born in abundance, and helium as well, along with a trace of lithium. The young universe is now a blazing plasma, a fireball of bright, ionized gas filled with a haze of electrons, protons, and helium nuclei. Light exists in plenty. Photons stream everywhere, but the universe is still opaque, like the inside of a star, because those free electrons keep scattering the light. Photons bounce from particle to particle, unable to travel freely. The cosmos glows brilliantly, but like an eternal fog-bound sunrise, light trapped in a dense mist. If there were eyes to see, they would witness brightness everywhere, but no clear forms, only a uniform radiance. Eons of expansion and cooling pass. The once blazing cosmos dims from white-hot to red-hot to a dull orange glow, like iron cooling in a forge. Finally, as the universe ages and expands, a critical threshold is reached. The temperature falls to a few thousand degrees, cool enough for electrons to calm down and be captured by atomic nuclei. One by one, electrons settle into orbits around hydrogen and helium nuclei. At that moment, the free charges that kept the universe opaque vanish, locked into neutral atoms. The fog clears. All at once, light is free. Photons that had been trapped, ricocheting endlessly, now stream across the universe unimpeded. The entire cosmos, once an endless furnace of scattered light, suddenly becomes transparent. A brilliant glow suffuses space, the first light able to travel unhindered. It is as though a cosmic dawn has broken. The young universe shines as a whole, a pale, orange-white radiance, bathing everything. This glow comes from everywhere at once, filling all of space with a release of pent-up illumination. For the first time in cosmic history, darkness truly ends. But as with all things in an expanding universe, the light does not stay bright for long. Space continues to stretch, and that initial brilliant glow begins to fade and redden. What was once a blinding fire all around slowly softens. The orange-white light slips to deep red, then to infrared, weakening and cooling as the universe grows bigger and colder. In time, the glow becomes invisible to any eyes that might someday open. Day has turned to twilight on a cosmic scale, and then to night. The photons released at the clearing of the fog still exist, but now they are mere whispers of their former selves, stretched into faint microwaves by billions of years of expansion. The universe is left with a gentle afterglow, an omnipresent memory of that early light, too dim for any creature to perceive without special instruments. This faint afterglow is what modern science calls the cosmic microwave background, a cool, all-pervading whisper from the universe's infancy, still murmuring in the darkness. It will persist through all cosmic time, a quiet testament to the moment the cosmos first revealed its light. For a long stretch after that first dawn, the universe has no new sources of illumination. The brilliant flash of creation has faded to an infrared and microwave murmur. To any hypothetical observer then, space would now appear black and starless. The cosmos has entered a deep cosmic night, a dark age before the first stars. Yet in this darkness, something profound is happening. The universe is no longer perfectly uniform. Tiny ripples in density, imprints from the universe's explosive birth, have begun to grow. Under the gentle but relentless pull of gravity, matter starts to gather into ever so slightly denser clumps. The primordial hydrogen and helium gas, spread almost evenly across space, finds itself ever so subtly thicker in some areas than others. Those areas draw in more gas from their surroundings. Invisible hands, gravity's hands, are sculpting the cosmic landscape. Vast swaths of gas begin to flow along unseen paths, collecting into filaments and nodules. In the darkness, the primordial cosmos is taking on structure. A cosmic web is emerging, though no one is there to see it. Slowly, ever so slowly, the darkness is seeded with the promise of light. Over millions of years, diffuse gas pools into clouds, and those clouds condense into tighter knots. Gravity sculpts filaments and knots in the diffuse gas, a delicate framework stretching across space. Where the filaments intersect, gas piles up into deepening gravitational wells. Dense pockets form like dew collecting on a web, and within them, pressure and heat begin to build relentlessly. Eons pass in darkness as these invisible battlefields of gravity and pressure play out, until, at last, gravity's relentless pull triggers a dramatic event. In one of these collapsing clumps of gas, a point of light ignites. Deep within a particularly dense cloud, hydrogen atoms are squeezed so tightly and heated so intensely that they begin to fuse together. Like countless nuclear bombs detonating each second, this fusion unleashes a brilliant flood of energy. A new star's fire is lit. After ages of darkness, a pinprick of starlight pierces the cosmic night. A star is born. The first star the universe has ever known. It's a massive, hot star, far larger than most that will come later. In its core, nuclear reactions burn furiously, turning hydrogen into helium and releasing a blinding radiance. Starlight bursts outward from that newborn star, and a radiant beacon now shines, where before there was only cold, silent gas. This lone star is soon joined by others. In neighboring dense pockets across the early universe, gravity ignites more stellar flames. One by one, throughout the cosmos, new lights flicker on as other gas clouds collapse and give birth to stars. They gather in clusters, the earliest proto-galaxies, tiny precursors to galaxies, each a swarm of newborn suns. Like lanterns kindling across a dark landscape, these first stars mark the end of the cosmic dark ages. The long night is over. The cosmos has had its first sunrise. The earliest stars are giants, colossal suns blazing blue-white with ferocious heat. They burn their fuel extravagantly, shining far brighter than the stars of later eras. But they live very short lives. They are born in a universe devoid of heavy elements, made only of primordial hydrogen and helium, which allows them to grow more massive than almost any stars that follow. These stellar leviathans pour out searing ultraviolet light that begins to clear the murk of leftover hydrogen gas around them. Ultraviolet photons rip electrons from hydrogen atoms in their vicinity, turning that gas back into hot ionized plasma. Each young star creates a bubble of transparency around itself, pushing back the curtain of remaining darkness. As more and more stars form, these bubbles expand and merge. Gradually, the flood of starlight rayonizes the cosmos, banishing the primordial gloom and making space transparent even to the fiercest ultraviolet rays. The universe, once a cold void, is now studded with brilliant fires. The lives of these first stars, though luminous, are tragically brief. In mere millions of years, a blink by cosmic standards, they exhaust their fuel. Inevitably, one by one, they begin to die. As a massive primordial star nears its end, its core can no longer sustain the fusion that holds up its great weight. With the fuel spent, there's no longer outward pressure to balance gravity's inward pull. The core of the star caves inwards in a matter of seconds, heating and compressing to unimaginable extremes. In many cases, this collapse triggers a colossal rebound. The star's outer layers rush inward, then violently explode outward. The star dies in a titanic supernova, a detonation so bright it can, for a brief time, outshine entire galaxies. For that brief moment of death, the star accomplishes something miraculous. It creates elements heavier than helium that never existed before in the cosmos. In the furious furnace of the supernova, atoms fuse into new kinds: carbon and oxygen, silicon and iron, gold and uranium, and many more. The dying star hurls these newfound treasures into space, along with its blazing guts of lighter elements. Its outer layers explode outward at incomprehensible speed, a shockwave racing through the surrounding darkness. What was once a tranquil, steady star becomes an expanding shell of incandescent gas, a supernova remnant, enriching the cosmic medium with the ash of newly forged elements. Some massive stars collapse so completely that their cores become black holes, regions of gravity so intense that not even light can escape. Others leave behind ultra-dense neutron stars, city-sized spheres of degenerate matter. But regardless of these exotic remnants, the most far-reaching legacy of the first stars is the enrichment of space. The heavy elements scattered by their supernovae spread out and mix into the surrounding gas. Without such stellar catastrophes, planets and life as we know them would be impossible. These first stars are cosmic alchemists. In dying, they forge the ingredients for worlds and living beings to come. Thus, paradoxically, the destruction of the earliest stars lays the groundwork for even greater complexity in the universe. The once pristine cosmic gas is no longer pure hydrogen and helium. It is seeded with new elements, metals, later generations of astronomers will call them. These added elements radiate heat more efficiently, allowing gas clouds to cool faster and fragment into smaller clumps. In the ashes of the first supernovae, enriched clouds of gas begin to collapse anew. The next generation of stars is born amid the debris of the first. While stars are being born and dying, gravity is orchestrating an even grander dance on larger scales. The first stars don't form in isolation. They gather in groups, bound by their mutual gravity. Dozens, then hundreds of these pioneers swarm together, forming star clusters that are the seeds of galaxies. Over time, more gas falls into these clusters, spawning new stars, and the clusters grow. Small proto-galaxies merge with their neighbors, drawn together like droplets of water coalescing on a window pane. With each merger, a new, larger galaxy takes shape, its form changing in the violent embrace. Two stellar systems may collide and pass through one another. Individual stars rarely crash head-on, given the vast space between them. But their gas clouds slam together, triggering brilliant bursts of star formation. In these cosmic collisions, galaxies are born and transformed. Rotating disks flatten out and sprout majestic spiral arms, or chaotic mashups settle into glowing ellipticals. The history of the universe is a history of structure emerging and growing. Clumps of matter becoming star clusters merging into galaxies, galaxies assembling into even larger galaxies. On a larger canvas still, gravity draws galaxies into communities. Galaxies are not scattered randomly. They collect in groups and clusters, and these clusters themselves clump along unimaginably long filaments. The matter in the universe forms a vast, foamy pattern, the cosmic web. Galaxies line up in gossamer threads and walls, outlining enormous voids where hardly any galaxies shine. Picture a sponge, or a spider's web, on the scale of hundreds of millions of light years. That is the distribution of galaxies in our cosmos. In this grand design, clusters of galaxies are nodes where filaments intersect, and between these bright nodes stretch sparse bridges of matter. The voids between are like black hollows, cosmic cavities, with only a sprinkling of galaxies inside. If we could view the universe from far above, we would see something like a luminous web or the neural network of a giant mind, galaxies linked by filaments across the dark. Yet, in this immense cosmic web, most of the matter is hidden from view. Every galaxy, every cluster of galaxies, sits within an enormous halo of invisible mass that far outweighs all the stars and gas we can see. This hidden mass is dark matter, an elusive substance that neither emits nor absorbs light. It slips through ordinary matter almost like a ghost, rarely interacting except through the force of gravity. But its gravitational influence is profound. Dark matter provided the scaffolding for structure to form in the first place. Long before stars ignited, vast clumps of dark matter were drawing in gas, herding it into the filaments and halos that became galaxies. Now, it holds galaxies together and keeps their fast-spinning stars from flying into space. We infer its presence because stars in the outer regions of galaxies orbit faster than they should if only visible matter existed. Something unseen is contributing extra gravity. We also detect it indirectly through gravitational lensing. Distant galaxies appear distorted or duplicated because light bends around massive concentrations of unseen matter, like a cosmic funhouse mirror. All the evidence whispers of a huge invisible presence. Dark matter is the silent architect of the cosmos on large scales, the unseen glue that binds the glittering galaxies into the cosmic web. Without it, the universe would be a very different, likely far emptier place. While dark matter pulls the cosmos together, another mystery pushes it apart. For eons, gravity reigned, slowing the expansion of space. But long ages after the Big Bang, the balance tipped. The expansion, which had been decelerating under gravity's drag, found a new impetus and began to accelerate again. Space itself seems to possess an eerie energy, a built-in pressure of the vacuum that shoves galaxies away from each other. We call this dark energy, though the name is merely a placeholder for something we have yet to truly comprehend. It is everywhere, hidden in empty space, gentle yet relentless in its repulsive push. Over time, dark energy's influence grew and came to dominate the universe's evolution. Distant galaxies, once merely coasting outward, are now racing away faster and faster as space expands ever more rapidly. The cosmic web is being stretched thin. The majestic clustering of matter is now facing a counterforce that, given enough time, will carry even the largest structures apart. In the end, dark energy promises that the universe will not remain as it is. It will rush onward, faster and faster, into a future of its own making. Now step back and consider the journey so far. A blazing birth, expansion, the formation of structure, stars flaring into existence and dying in glory. Underlying it all is an irreversible flow, the arrow of time. Why does time move ever forward, never backward? Because the universe progresses from order to disorder, from a smooth beginning to an ever more complex yet increasingly disordered state. The early cosmos was hot, dense, and astonishingly uniform. Despite its ferocious energy, in some sense it was simple and low in entropy, highly ordered. Over time, contrasts emerged, structure formed, and energy spread out. Entropy, the measure of disorder, has been steadily increasing. This one-way increase of entropy is the script that time follows. It's why stars exhaust their fuel and burn out instead of refueling and burning backward. It's why glass shatters and never unshatters. Why we grow older and never younger. The universe's expansion and the gradual winding down of energy distributions set a direction to time like an arrow fired from a bow. Every supernova scattering star stuff into space, every photon streaming into the night, and every galaxy carried farther apart by expansion. Each event is one more tick of time's arrow, an irreversible step from what was to what is to what will be. The past is fixed behind us, the future unknown ahead. And yet, within this grand drift toward disorder, something remarkable has happened. Complexity has blossomed. The same laws that mandate increasing entropy also allow local pockets where entropy decreases, as long as greater disorder is produced elsewhere. In the aftermath of the first star's deaths, enriched clouds of gas could cool and fragment more efficiently, giving rise to intricate star systems with planets and moons. Out of these materials, on at least one small world in the vast darkness, atoms began to assemble into elaborate structures that could grow and replicate. Against the backdrop of a cooling, expanding universe rushing towards simplicity, complexity took root. There arose molecules that could copy themselves, tiny flickers of order sustained by feeding on sunlight and the warm chemistry of oceans. Life had begun. In warm little ponds, or perhaps around undersea hot springs on that young world, the first living cells emerged, microscopic, membrane-bound droplets carrying out primitive chemistry. These were the humble ancestors of all future life, utterly simple, and yet already striving and evolving, sustained by the energy of their parent star. From simple single cells, life on that blue world grew more intricate with time. Some microbes learned to harness sunlight. New oxygen flooded the skies and transformed the planet. Single cells joined together, forming multicellular beings. Life swarmed in the seas and eventually crept onto the barren land. There were times of exuberant diversification and times of mass extinction, but some living threads always survived to continue the story. In due time, after billions of generations of subtle improvements, sensing, thinking, creatures emerged. Beings with eyes to see and minds to wonder now walked under the stars. Out of molecules that once danced aimlessly in primordial oceans, consciousness sparked into existence. With that, the universe, in a small corner of itself, became aware. Through these curious beings, matter gained the ability to reflect on itself, to feel awe at the sky above, to seek meaning in the stars. The cosmos, which began in unconscious darkness, now had eyes to behold its light and ask its own nature. From the moment those beings gained the spark of awareness, the stars called out to their curiosity. Early on, around primal campfires, they crafted stories about the sky, a great domed tapestry of lights set there by gods or ancestral spirits. The sun and moon became characters in their myths, and the glowing band of stars overhead was seen as a river of milk or the pathway of souls. They had no idea what those points of light truly were, yet the mystery itself captivated them. Over many generations, their questions only grew deeper. They learned to track the wandering planets, to predict eclipses and the changing seasons. Curiosity begat observation, and observation begat science. They built tools, first simple charts and astrolabes, later telescopes that could magnify the heavens, and spectroscopes to break starlight into rainbows. With each step, the cosmos revealed more of itself. The morning star in the dawn sky proved to be a world like their own. Fuzzy patches of light in the dark turned out to be entire galaxies. Bit by bit, these descendants of the primordial life began to piece together the tale of the universe. They uncovered the age of rocks and the sun, learned the language of mathematics and light, discovering that simple equations could predict the motions of planets and the behavior of energy. They saw farther in space and time than eyes alone ever could, out to distant galaxies and back to the universe's fiery birth. In modern times, humanity has catalogued galaxies billions of light years away and detected whispering signals left over from the birth of the cosmos. In doing so, we found that reality is grander than any myth our ancestors once imagined. Having come this far, these curious beings begin to ask grand new questions. They measure the sky with their instruments and ponder what they find. They wonder, is our universe the only one, or just one chapter in an endless library of universes? What lies beyond the edge of what we can see? Does space go on forever, or does it curve back on itself like a gigantic sphere? If one could travel in a straight line through space indefinitely, would one loop around and end up back where one started, or simply wander endlessly into eternity? Imagine setting off in a spaceship, never turning, never stopping. Would you travel onward forever, passing galaxy after galaxy without end? Or after unimaginable distances, might you find yourself back where you began, arriving from behind as space curves in a great cosmic loop? Thus far, the universe reveals no edge, no sign that our cosmic ocean ends or that space wraps around. As best we can tell, space is either truly infinite or so vast and uncurved that it might as well be. Our observable universe is bounded only by the distance light has traveled since the beginning, not by any physical border. The horizon we see is not a wall, only the limit of vision. There is almost certainly more beyond, forever out of reach. Perhaps far beyond our sight, other regions exist, too distant for their light to ever reach us. They could be fundamentally similar to our observable universe, with galaxies and stars, or perhaps different in ways we cannot imagine. In either case, the part of the universe we can see may be only a tiny patch in a vastly larger cosmos, possibly an infinite expanse. Some thinkers even imagine that our Big Bang was not unique. Perhaps it was one bubble in a foam of countless Big Bangs. Maybe new universes sprout like fireflies in the night, little pocket realities that explode into being, each with its own space, time, and laws of physics. In this scenario, called the multiverse, our universe might be just one bubble among an endless sea of others frothing into existence in a timeless cosmic ocean. In one universe, gravity might be a bit stronger. In another, stars might never form at all. Ours just happens to have the right conditions to birth galaxies and life. Or consider another idea. Every time a decision is made or a quantum event has multiple outcomes, perhaps reality splits, each possibility spawning its own universe. In this view, existence is like a mighty river that keeps branching into countless streams, creating an ever-multiplying array of parallel worlds. These ideas are speculative, verging on the philosophical, perhaps forever beyond empirical reach. Yet they remind us that reality could be far grander and more varied than we know. What we see might be a mere spark in an endless fireworks display of universes. And what of our universe's own fate? Every story, it seems, has an end. Will the cosmos simply expand forever, growing ever colder and darker? Or will it end in fire and fury, or perhaps in a rebirth? Gazing into the far, far future, we can imagine a few possible finales for this grand cosmic drama. In one vision, the expansion never stops. The galaxies drift farther and farther apart, the stars within them burn out one by one, and no new lights replace them. The universe becomes an increasingly cold and lonely place. Trillions of years from now, the great galaxies that adorn the night sky today would be invisible to any future observer, sped so far away that their light no longer reaches us. Long after that, the stars within our own galaxy would age and die. The cosmos would be littered only with their corpses, white dwarfs, neutron stars, and black holes. Eventually, even those remnants will cease to shine or will wink out of existence. White dwarfs cooling to black holes slowly evaporating over mind-boggling timescales. All matter might decay into the subatomic and disperse. What remains is a thin, cold haze of particles and dilute radiation, expanding into endless nothingness. This is the fate known as heat death, the big freeze, a universe eternally dying, yet never quite dead, asymptotically approaching nothingness. If you were an immortal being drifting in that far future, you would see an empty darkness like no night ever known. Galaxies beyond your own would have vanished from sight eons earlier. You might roam an entire galaxy and not find a single living star, only cold embers, black dwarf cinders, neutron stars, and silent black holes lurking invisibly. The very atoms of your body and surroundings would be decaying, proton by proton, over unimaginable spans. It would be a silent, frigid expanse, with nothing to mark the passage of time except the gradual fading of whatever faint glow of warmth still clings to existence. It is a lonely, ghostly end, the cosmos as an eternal winter, quiet and still. In another vision, the opposite happens on the grandest scale. The expansion itself might one day rip everything apart. If the mysterious dark energy grows stronger with time, as some theories allow, it could eventually overwhelm every binding force. In the far future, galaxies wouldn't just drift apart, they would accelerate away at phenomenal speeds. Gravity would lose its grip even on individual galaxies. Stars would speed out of their orbits around the galactic center. Planets would fly off from stars. Ultimately, in the last moments, even atoms could be torn asunder, ripped apart by the expansion of space itself. Space would literally rupture. in a final catastrophic burst of all structures. The Big Rip, a cosmic dissolution of all order. Such an end would be as violent as it is swift. If you lived in a time approaching a Big Rip, you would witness a bizarre and terrifying sequence of events. Galaxies that once glimmered in the night would vanish, one after another, as the fabric of space carried them beyond your horizon. Then your own galaxy would stand alone in the darkness, all others gone. In the final weeks or days, that darkness would start to brighten strangely, not from new light, but because the stars of your galaxy itself are flinging outward past you, leaving you amid fewer and fewer neighbors. The night sky would grow increasingly black as stars stream away into the void. Then, perhaps only your star system remains. In the last minutes, planets might slip from their orbits. The moon might spiral away from its planet. In the final seconds, the planet itself could come apart beneath your feet, crust, oceans, and core flying off as space tears it loose. You too would not be spared. First, pulled apart into molecules, then atoms, then subatomic bits, until even those are ripped from one another. In a big rip, the cosmos unmakes itself violently, a swift and total disintegration where all of creation's threads are unraveled into nothing. There is also a more circular vision. Perhaps gravity will one day halt the expansion and draw everything back inward. In this scenario, the cosmos would reach a maximum size, and then, ever so slowly, begin to contract. Galaxies would start to converge. Distant clusters would grow larger in the sky as they come hurtling closer. Over unimaginable spans of time, all matter and space would crunch back together. The universe that began in a bang of creation could end in a crunch of destruction, a big crunch, where space collapses into a hot, dense state once more. Some speculate this could even lead to a bounce, to a new Big Bang born from the old universe's ashes, making the cosmic story cyclical, an infinite series of expansions and contractions. If the cosmos were destined for a big crunch, the far future would grow brilliant and hot instead of cold and dark. Imagine billions upon billions of years hence. The expansion has not only stopped, but reversed. Galaxies begin rushing together. The night sky, now dark in our era because of immense distances, would start to brighten as more galaxies crowd into view. Thousands, then millions of galaxies, shining with the light of their trillions of stars, would fill the heavens. As time goes on, these galaxies would collide and merge, and the sky would blaze with the light of star formation everywhere. The cosmic background glow that is now a cold, faint microwave whisper would heat up to a warm glow, then to a furious glare, as all light becomes compressed in the shrinking universe. Eventually, all galaxies would coalesce into a single, all-encompassing fireball. In its final moments, everything, every atom, every star, every black hole would crash together. The universe would become an unimaginably hot, dense point once again. It would be as if the universe was rewinding to its beginning. The final heartbeat of this cosmos might echo the first, ending in a silent, searing singularity. Perhaps, as some hope, that final collapse could be a rebirth, an implosion that triggers a new explosion, a new Big Bang, with a new universe emerging phoenix-like from the old. Or perhaps it truly would be the end. A brilliant flash of everything, then absolute silence. No one yet knows which fate awaits our universe. Endless expansion and freezing, a violent ripping apart, a grand collapse and potential rebirth, or some other end we have yet to imagine. For now, we live in a precious era of cosmic history. Enough time has passed since the beginning for galaxies, stars, planets, and life to have formed, but expansion has not yet accelerated, so much as to plunge everything into darkness. We exist during the cosmic midday, when the sky is rich with galaxies and the afterglow of creation still faintly lingers all around us. We can study the cosmos in this fortunate time and piece together its past, glimpse its possible futures, and marvel that we are here, alive and aware, witnessing the universe in its splendor. In our quest to understand reality, we have discovered that the familiar is not what it seems. Deep down, matter is not solid, and empty space is not truly empty. Everything is made of underlying fields, not tangible particles. One can imagine these fields as the hidden instruments of a grand cosmic symphony, each particle a fleeting note arising from the vibrational mode of a field. The vacuum of space is more like a silent stage filled with the potential for music. What appears empty is in fact a medium filled with invisible fields, electric fields, magnetic fields, gravitational fields, and more, that permeate all of existence. A particle is really a localized ripple in these fields, a little wave carrying energy. Thus, every atom in our bodies is a tiny vibration in a field that spans the universe. Even the void seethes with quantum whispers. Virtual particles flit in and out of existence, a restless sea of possibility beneath the veneer of nothingness. The closer we examine reality, the more it dissolves into a mesh of energy and information, a phantom dance of fields and probabilities. Space and time, too, have revealed their intimate strangeness. They are not rigid, separate backdrops to events, but a unified, flexible fabric, space-time, that can bend, stretch, and wrinkle. Mass and energy warp this fabric. A massive body like the Earth or the Sun creates a dimple in space-time around it, causing passing objects or beams of light to curve as they go by. Time itself can slow down or speed up depending on conditions. A clock on a speeding spacecraft ticks more slowly relative to one at rest. A second near a black hole can last longer than a second far from it. If you were to hover near the edge of a black hole's gravity, you would experience time passing normally for you, but an outside observer might see your movements stretched and slowed enormously. Space and time are malleable. When massive stars dance and merge in the depths of space, they send faint tremors through the fabric of space-time, gravitational waves that ripple outward like the surface of a pond disturbed by a stone. We have learned to hear these whispers of space-time. In giant detectors on Earth, we've caught the subtle stretching and squashing of space itself as black holes in distant galaxies collided and made the very planet quiver by less than the width of an atom. Reality, it turns out, is far more fluid and surprising than our everyday senses suggest. And through it all, filling the backdrop of the cosmos, is that gentle glow from the beginning of time. Once a brilliant flash of newborn light, now stretched to a cool whisper, it bathes the entire universe. It is a cool remnant of the fireball era, a billboard in the sky quietly proclaiming our origins. We are immersed in this ancient light at every moment, warmed imperceptibly by photons that have been traveling for nearly the universe's entire lifetime. The past is never fully gone. It surrounds us, humming softly just beyond our vision. Even in the stillness of a moonless midnight, with the stars glittering overhead, the air around us carries the faint whisper of the Big Bang. Here, on this tiny blue world, orbiting an unremarkable star in the outskirts of an ordinary galaxy, the universe has opened its eyes. We find ourselves alive, aware, and filled with questions inside a cosmos so vast and ancient that our minds strain to grasp it. We feel small beneath the sprawl of stars overhead, yet we are intimately connected to them. The very substance of our bodies was forged in stellar furnaces and spread through space by stellar deaths. The calcium in our bones was forged in the belly of a supernova and cast into the galaxy before condensing into the world that would one day become our home and finding its way into our bodies. The iron in our blood once dwelt in the core of a massive star long ago. It rode the shock wave of that star's explosion, floated through interstellar space, and eventually became part of the dust and rocks that built this planet. The carbon in our DNA was cooked in the hearts of dying stars and released into the galaxy, wandering for eons until incorporated into the cells of our ancient ancestors, and now into us. Every atom in your body has traveled through time and space to be part of you. When we say we are made of stardust, it is the literal truth. We are made of this cosmos. We are built from its history. We are a way for stardust to contemplate the stars, for the cosmos to know itself. With our minds awakened, we have peeled back layers of time and space, determined to understand our origins. We have found that the universe is even more majestic and mysterious than those early sky watchers around the fire could have imagined. We have sent probes to other worlds and seen our planet from afar, a pale blue dot suspended in darkness, realizing how small and precious our home is. We have built great observatories that collect the ancient light from the beginning of time, and particle accelerators that recreate conditions just after the Big Bang. Every question we answer leads to deeper questions, but each discovery brings us a bit closer to the truth of our origins. Through science and art, through myth and mathematics, we continually translate the cosmos into terms we can understand. We create music and poetry inspired by the stars, and equations and theories to explain them, all in an effort to express the inexpressible. In doing so, the universe is writing its story through us. Our art, our science, our curiosity and creativity, they are the universe's way of reflecting on itself. What is the universe? It is an unfinished story, both out in the heavens and within our own minds. It's the totality of all that is, matter and energy, space and time, and also the emergent experiences those give rise to, like beauty and love and curiosity. It is every galaxy that twirls, every star that shines, every life that lives. It's the roar of the Big Bang and the quiet whisper of a human heart pondering the cosmos late at night. It is, in a sense, the universe asking itself what it is. We, tiny motes of consciousness on a small planet, carry the torch of this grand story forward. We are the narrators and also characters in the cosmic epic. In seeking to find our place in it, we find that we are it. We are not separate from the universe at all, but an inseparable part of its unfolding. The universe is inside us, made of us, as much as we are inside the universe. Its story is our story. In the end, the universe is a grand cosmic symphony, and we are a brief but vital motif within it, yet integral to its music. As we live and love, explore and create, we add our own notes to this ongoing composition. The music began long before we arrived, and will continue long after we are gone. But for this fleeting moment, we can listen to it, we can marvel at it, and we can even play our part. Through our ears, the universe listens to its own harmony. Through our eyes, it gazes upon its own magnificence. Through us, the universe feels wonder. As we gaze into the darkness sprinkled with ancient light, we cannot help but feel a profound connection. The atoms of our bodies were born in stars. Our thoughts are shaped by laws that govern galaxies. We are the universe, awake, curious, and able to ponder itself. In our brief lives, in our questions and dreams, the cosmos achieves a form of self-awareness. The story of the universe is still unfolding, and we are chapters in its narrative, co-authors of its next verse. So, what is the universe? It is more than a collection of galaxies and particles and physical laws. It is an experience, an ongoing, mysterious experience that includes the rise of conscious beings who can ask that very question. It is the primordial darkness and the burst of light. It is the weaver of space and time and the tapestry woven. It is the question and the desire to understand. It's the infinity that birthed us and that we now reach for in our thoughts. The universe is the grandest of all stories, the story of everything. And through our questions, our explorations, and our awe, that story continues. The universe is still writing itself through us. Each of us, with our wonder and our creativity, is a means for the cosmos to know itself and to continue its epic. In the final reckoning, the most beautiful creation of the universe may not be a star or a galaxy, but the very capacity to appreciate its wonders. We are the universe's way of marveling at its own majesty. And as long as there are beings to look up at the sky and feel awe, the universe's story will never truly end. The story of galaxies. Cosmic cities in the night. On a clear, moonless night, far from city lights, the sky becomes an infinite ocean of darkness studded with stars. Across that darkness arches a pale, luminous band, a gauzy river of light flowing from horizon to horizon. For millennia, humans have looked up at this silvery band with wonder. In myth and legend, it became a celestial road for the gods, a river of souls, or the spilled milk of a goddess strewn across the heavens. Before our cities lit the night and banished the stars, the Milky Way was a canvas for our imagination and a mirror of our yearning. People around the world named it in their own poetic terms: a straw way dropped by heavenly farmers, a silver river bridging lovers, a sky road for migrating birds, a spirit path for departed souls. Yet, even in their enchantment, those early stargazers could not imagine the true nature of that milky band. It would take centuries to discover that every wisp of that glow comes from countless distant suns, and that beyond the Milky Way lie other cosmic cities of stars, faintly visible as tiny smudges in the sky. What are these great star cities, these galaxies, that form the grand architecture of the universe? How did we come to understand them, and what do they tell us about our own existence? Our journey begins with the story of how humanity slowly awakened to the true scale and wonder of the galaxies. From myth to discovery, the Milky Way and beyond. For most of human history, the Milky Way was a mystery. Even as ancient myths wove stories about its light, no one knew what it truly was. The breakthrough came in 1610 when Galileo Galilei turned his telescope to that milky band. What he saw astonished him. The smooth glow dissolved into countless faint stars. The Milky Way was not a cloud or the breath of gods. It was made of stars. This was our first glimpse of the galaxy's true nature. Still, the Milky Way was thought to be the entire universe, a lone island of stars in a vast, dark sea. As the centuries passed, a few bold thinkers began to suspect there might be more islands out there. In 1755, philosopher Immanuel Kant imagined that the faint cloud, like patches observed in the night sky, were actually other Milky Ways, island universes far beyond our own. In the 1800s, telescopes grew more powerful, and astronomers began to see structure in these mysterious patches. The Great Irish Telescope of Lord Rosse, for example, revealed a spiral form in the Whirlpool Nebula in 1845, a majestic pinwheel of light. Such sightings fueled speculation. Could these spiral nebulae be galaxies in their own right? Colossal systems of stars as vast as the Milky Way? The idea was daring and controversial. Many scientists insisted these nebulae must be nearby clouds of gas or clusters within our Milky Way, because imagining them as separate galaxies made the universe seem unthinkably large. Meanwhile, our understanding of the Milky Way itself was growing. In 1785, William Herschel attempted to map the Milky Way by counting stars in every direction, sketching our star system as a vast, flattened disk. Later, in the early 1900s, astronomer Harlow Shapley used pulsating stars in globular clusters to measure distances across the Milky Way. He discovered that those clusters formed a great halo, centered not on Earth, but far off in the direction of the constellation Sagittarius. In other words, the center of the Milky Way was nowhere near our solar system. Our sun was tucked in the suburbs, tens of thousands of light years away from the galactic center. The Milky Way, Shapley found, was enormous, on the order of 100,000 light years across or more, and our place in it was humble. Yet the true nature of the spiral nebulae still hung in the balance. Were they part of this one huge galaxy, or separate galaxies altogether? On April 26, 1920, in Washington, D.C., a crowd gathered at the Smithsonian's Museum Auditorium to hear a public debate about the scale of the universe. It was a historic showdown. Two astronomers, Harlow Shapley and Heber Curtis, argued over the scale of the universe. Shapley, armed with his measurements of the Milky Way's vast size, believed our galaxy was the only galaxy. Everything we saw, including the spiral nebulae, lay within it. Curtis, however, maintained that the nebulae were far outside our galaxy, perhaps as other galaxies unto themselves. They traded evidence before an audience, posing a profound question. Was the universe essentially one galaxy, or was our Milky Way just one of many? The answer arrived only a few years later, from the Mount Wilson Observatory in California. There, in 1923, astronomer Edwin Hubble peered through a 100th-inch telescope, then the world's largest, and examined the Andromeda Nebula in exquisite detail. Amid the hazy glow of Andromeda, he identified a faint, Cepheid variable star, a type of star that waxes and wanes in brightness in a regular rhythm. Cepheids are valuable cosmic yardsticks. Their pulse period reveals their true brightness, which in turn can be used to calculate their distance. When Hubble calculated how far away this star was, the result was staggering, roughly 2.5 million light years. Far beyond the Milky Way's boundaries, Andromeda wasn't a nearby cloud at all. It was an entire galaxy of its own. Hubble's discovery was a watershed moment. It's said that upon seeing Hubble's evidence, Shapley conceded with awe, "Here is the letter that has destroyed my universe." The paradigm had shifted. The Milky Way was no longer the entire cosmos, but one galaxy among a multitude. In one stroke, the universe became immensely larger. The Milky Way was revealed to be just one galaxy among many. In the wake of Andromeda's measured distance, other spiral nebulae were likewise found to be far outside the Milky Way. Those tiny smudges and whirlpools on photographic plates resolved into myriad galaxies, each an island of stars. Our one-island universe had become an archipelago of galaxies, scattered through an expanding cosmos. By the mid-20th century, it was clear that the universe is teeming with galaxies. Astronomers began to catalogue the galaxies by the thousands, then millions. Estimates of the total number of galaxies climbed into the billions. Edwin Hubble himself, after proving the existence of other galaxies, went on to observe that galaxies are rushing away from one another, evidence that the universe is expanding from a primordial beginning. But it all started with that realization that the Milky Way is not alone. The word galaxy, once synonymous with our Milky Way, now described an entire class of colossal star systems. The night sky's faintest whispers of light became mighty galaxies in our understanding. In the span of a few decades, humanity's view of the cosmos was transformed. We went from a universe confined to one galaxy to a universe filled with countless galaxies stretching in all directions. The revelation was as humbling as it was exhilarating. Our Milky Way, with its billions of stars, was just one among billions more. The scale of creation had expanded beyond imagination. The stage was set to explore these newfound galactic realms, to ask what galaxies are made of, how they live and die, and what role they play in the grand story of the universe. Anatomy of a galaxy, stars, dust, and dark matter. What does a galaxy actually look like, up close? Picture a giant rotating pinwheel made of stars. In a typical spiral galaxy like our Milky Way, billions of stars are arranged in a flat, pancake-shaped disk that revolves around the center. Graceful spiral arms wind outward from a bright central region like glittering trails. Those arms are not solid arms at all, but patterns, density waves, where stars and gas bunch together. They mark where new stars are being born, lighting the arms with young, blue starlight and the pink glow of nebulae. Traces of dark, filamentary dust clouds weave through the arms, silhouetting the starlight. Closer to the center of the galaxy, the spiral arms give way to a bright central bulge, a crowded spherical hub of older reddish stars. At the very heart of that bulge, in the nucleus of the galaxy, lurks a powerful presence, a supermassive black hole. This monster, millions of times the mass of the Sun, anchors the core. Most of the time, it's invisibly quiet, swallowing the occasional drifting star or gas cloud. But it's there, a dark heart at the center of the galaxy's light. Surrounding it is a dense swarm of stars in the bulge, orbiting like bees around an unseen queen. Moving outward from the bulge, we transition into the disk of the galaxy, the broad, flat region where the spiral arms sweep around. Here is where the majority of a spiral galaxy's stars reside, including our own Sun. These stars orbit the galactic center in nearly circular paths as the entire disk rotates majestically. Our Sun, for instance, takes about 230 million years to complete one circuit around the Milky Way's center. Throughout the disk, we find vast clouds of gas and dust, the raw material for new stars. In fact, the spiral arms themselves are sites where this gas and dust have been compressed, triggering the birth of clusters of stars. It's within these stellar nurseries that bright young stars form and burn hot, illuminating their surroundings. Beyond the visible disk of stars, a galaxy extends further into a much fainter realm. Enveloping the galaxy is a vast halo of old stars, globular clusters, and something even more mysterious: dark matter. Scattered throughout this halo are ancient globular clusters, each a spherical swarm of very old stars orbiting the galaxy's center. The halo's stars are scarce and dim, so you'd barely notice them in a photograph. But the halo isn't empty. It's filled with an enormous amount of invisible mass. This is the galaxy's dark matter halo, a spherical cloud of matter we cannot see, but whose gravity we can feel. It's this dark matter that provides much of the gravitational glue holding the galaxy together, extending well beyond where the starlight fades out. In a real sense, the true size of a galaxy is defined not just by its starlight, but by this huge dark halo reaching far into space. All these components, the spinning disk with its spiral arms, the central bulge and black hole, and the extended halo of stars and dark matter, together form a single coherent system bound by gravity. A galaxy is like a cosmic ecosystem. Stars are born from gas, live out their lives, and die, often exploding and enriching the galaxy with heavier elements. Those elements mix into new gas clouds, seeding the next generation of stars. Over billions of years, this cycle of birth and death gives the galaxy its character. In our Milky Way, for example, generations of stars have come and gone, forging the elements that now make up our Sun, our planet, and even our bodies. Not every galaxy has the same structure, of course. Spirals like the Milky Way have distinct disks and arms. Other galaxies, called elliptical galaxies, are shaped more like rounded or football-shaped swarms of stars with no obvious disk or arms, essentially just big, puffy collections of stars. They tend to contain older stars and little gas and dust. And then there are irregular galaxies, which defy neat classification, with chaotic shapes often caused by gravitational encounters or mergers. But all galaxies share the same basic ingredients: stars, gas, dust, and dark matter, arranged in some unified form. Whether a galaxy is a flat spiral or a blob like elliptical, It will likely have a central concentration of stars and a surrounding halo dominated by dark matter. In a way, a galaxy is like a city of stars. It has a densely populated downtown, sprawling suburbs, and distant outlying regions that fade into the darkness. It is an enormous, self-contained society of stars orbiting together through space. Our Milky Way, for instance, contains hundreds of billions of stars, each as real and potentially as sun-like as our own, along with vast interstellar clouds and invisible dark matter. Yet despite this richness, on the scale of a galaxy, space is mostly empty. Stars are so far apart that if you shrank the Milky Way to the size of an earthly city, each star would be like a single grain of sand, separated from the next grain by blocks or miles of empty space. From the central black hole to the far-flung halo, a galaxy is a complex, gravitationally bound system. Every part affects the others. The black hole can influence the surrounding bulge. Supernova explosions from dying stars enrich the gas that forms new stars, and the dark matter's gravity guides the orbits of stars in the outskirts. This grand structure, stars, dust, gas, and dark matter dancing in unison, is what makes a galaxy more than just a random collection of matter. It's a self-organizing cosmic city, one that evolves and changes over time, but remains bound together by the inexorable pull of gravity. In the next part of our journey, we will look at how astronomers classify these galactic cities by their shapes and what those shapes reveal about the galaxy's histories. Galactic diversity, spirals, ellipticals, and irregulars. Galaxies come in a dazzling variety of shapes and sizes. In the early 20th century, Edwin Hubble devised a system to classify them, often depicted as a tuning fork diagram. At one prong of the fork are the elliptical galaxies, big, smooth balls of stars ranging from nearly round to elongated ovals. On the other prong are the spiral galaxies, flat disks with spiral arms, further divided into those with a central bar of stars and those without. In between, bridging the fork's handle to the prongs, are lenticular galaxies, disk, shaped like spirals but without visible arms, appearing as a smooth lens of stars. And off the neat ends of the fork are the oddballs, irregular galaxies that don't fit any simple shape. The spiral galaxies are perhaps the most visually striking. They look like cosmic pinwheels, with curving arms and sometimes a bar through the center. Our Milky Way is one such barred spiral, as is the nearby Andromeda galaxy. Spirals tend to have plenty of gas and dust, which fuels ongoing star formation in their arms. The presence of bright young blue stars and glowing nebulae gives the arms a speckled bluish tint, while the central bulge shines yellow, white with older stars. Spirals can have arms that are tightly wound or loosely trailing, and a given galaxy might have two prominent arms, or multiple fragmented ones. Despite these differences, when you see that classic spiral form, you're looking at a galaxy that is actively creating stars and has a dynamic, rotating disk. Elliptical galaxies, by contrast, are more like cosmic rugby balls or giant glowing halos. They lack the clear features of spirals: no arms, no disk, just a broad ellipsoid of stars. Some ellipticals are nearly spherical, others are stretched and elongated. These galaxies typically appear reddish or yellowish because they are dominated by older, cooler stars. Very little cold gas or dust remains in an elliptical, which means new stars are no longer forming there. Instead, an elliptical galaxy is a more quiescent system, a retired galaxy in terms of starbirth. Many ellipticals are also enormous. Some of the largest galaxies in the universe are giant ellipticals like M87 in the Virgo cluster, a monster galaxy with trillions of stars and a supermassive black hole at its core. These leviathans often sit in the cores of galaxy clusters, having grown by gobbling up smaller galaxies over time. Sitting between spirals and ellipticals are the lenticular galaxies. A lenticular galaxy has a central bulge and a disk like a spiral, but no spiral arms. It's as if the whirlpool pattern of a spiral galaxy has faded away, leaving just a smooth disk. Lenticulars often have used up or lost much of their gas, so they have little ongoing star formation, similar to ellipticals in that sense. Yet they still retain a flattened disk structure of stars. They might represent a transitional phase, perhaps a spiral galaxy that lost its gas, or maybe the product of mergers that didn't completely randomize the stars into a puffball. They tend to have older stars like ellipticals, and without arms they look more featureless, just a bright core and a faint disk fading outwards. Then there are irregular galaxies, which, as the name implies, refuse to be neatly categorized. Irregulars have ragged, blobby shapes with neither arms nor smooth symmetry. Many are small dwarf galaxies that simply don't have enough mass to form an organized structure. They might look like clumps of stars and gas without a clear center. Others have been distorted by gravitational encounters. A past close pass or collision with another galaxy may have torn them into chaotic shapes. The large and small Magellanic Clouds, companion galaxies to the Milky Way visible in the southern hemisphere's night sky, are classic examples of irregular galaxies. They are full of active star formation and nebulas, but lack the symmetry of a spiral. Irregulars remind us that not every galaxy is a majestic pinwheel or a serene ellipse. Some are cosmic train wrecks or nascent fragments still finding their form. These shapes aren't just cosmetic. They tell a story about a galaxy's history and life cycle. A spiral galaxy's supply of gas and abundance of young stars suggests it's in an active phase, still evolving gradually and relatively undisturbed. An elliptical galaxy, full of old stars and little gas, likely has experienced a more violent past. In fact, astronomers believe that many ellipticals are the result of galactic mergers. When two spiral galaxies collide and merge, the immense gravitational chaos can scramble their disk structures and trigger bursts of star formation that eventually use up the gas. The end product is often an elliptical galaxy, a big ball of stars that used to be two separate spirals. In the dense environments of galaxy clusters, where collisions are more frequent, we see many ellipticals, hinting at this violent upbringing. Lenticular galaxies might tell another evolutionary tale, perhaps a spiral that slowly lost its spiral arms. Imagine a spiral galaxy that falls into a cluster of galaxies. As it plows through the hot gas in the cluster, it can be stripped of its own gas. With its star, forming fuel removed, its arms would fade and cease to be obvious. What remains would be a lenticular, a disk of mostly older stars, quietly flying on without the youthful sparkle of arms. Thus, a galaxy can morph from a star, forming spiral into a more passive lenticular if the conditions take away its gas. Over time, even that disk might puff up through minor collisions or dynamic interactions, potentially becoming more elliptical. Irregular galaxies often represent youth or disruption. Some could be young galaxies that haven't settled down. In the early universe, many galaxies were clumpy and irregular before they coalesced into spirals or ellipticals. Others are simply what happens when galaxies gravitationally torment each other. An otherwise normal spiral can be twisted out of shape by a close pass with another galaxy, becoming irregular in the aftermath. In that sense, irregulars sometimes are like the before and after snapshots of galactic evolution, the building blocks that will later form larger galaxies, or the mangled remnants after a collision. Galactic morphology is a bit like a family album of galaxies. Spirals with their youthful star, forming glow, ellipticals with the faded glimmer of old age, and lenticulars and irregulars as the in-betweens and outliers. By classifying galaxies, astronomers glean insight into how galaxies live and change. We see that galaxies are not static. They can transform. Graceful spirals can merge and swell into giant ellipticals. Small dwarfs can be cannibalized by bigger galaxies. Collisions can shatter a galaxy's symmetry or spark new stars. The shape we observe, is a snapshot of a galaxy's ongoing story. This diversity in form is a testament to the myriad paths galactic evolution can take. It reminds us that each galaxy we see in the telescope, whether a perfect spiral or an amorphous smudge, has a unique history written in its shape and stars. Understanding these classifications and what they imply sets the stage for exploring how galaxies are born, grow, and sometimes die, a story that begins in the aftermath of the Big Bang and continues to unfold across cosmic time. Origins and evolution, from the Big Bang to today. Galaxies have not always filled the universe. There was a time, shortly after the Big Bang, when no galaxies existed at all, no stars, no structures, just a hot, dense fog of energy and subatomic particles. But even in that primordial chaos, tiny ripples in density were present. As the universe expanded and cooled, these slight fluctuations, quantum wrinkles stretched to cosmic scales, became the seeds of all future structure. Gravity began to amplify them. Regions just a bit denser than average slowly pulled in more matter. In the earliest epochs, matter in the universe was mostly hydrogen and helium gas, along with a much larger share of invisible dark matter. Dark matter doesn't interact with light, so as the universe cooled, it was free to clump together quickly, unhindered by radiation pressure. It formed an invisible scaffolding, a cosmic web of filaments and knots, into which ordinary gas flowed. Within a few 100 million years after the Big Bang, some of these knots of dark matter and gas had grown dense enough to ignite the first stars. These stars, we call them population 3 stars, were unlike any that exist today. They were likely extremely massive, bright, and short-lived, made of pristine hydrogen and helium. They lived fast and died young, some exploding as supernovae that enriched their surroundings with the first heavier elements like carbon, oxygen, and iron. With the birth of the first stars, the first proto-galaxies emerged. They might not have looked like the grand galaxies we see now. More likely, they were small, clumpy collections of stars. Perhaps only thousands or millions of stars bound together. But they were the seeds of future galaxies. Over the next few 100 million years, these fledgling star clusters began to merge and gather. Gravity drew proto-galaxies toward each other, combining them into larger structures. By 1 billion years after the Big Bang, the universe was becoming a cosmic cityscape of early galaxies. Many of them were irregular and turbulent, actively forming stars at a ferocious rate. The ultraviolet light from these newborn galaxies helped end the cosmic dark ages by ionizing the hydrogen gas in intergalactic space, making the universe transparent to starlight. As time went on, small galaxies merged into larger ones in a hierarchical fashion, like streams converging into rivers. This process of hierarchical merging meant that big galaxies grew at the expense of smaller ones. Every merger was a dramatic event. When two galaxies collided, their stars typically passed by each other, but their clouds of gas slammed together, triggering bursts of new star formation. The merging galaxies' shapes distorted, sometimes coalescing into a new form. Through countless such mergers and acquisitions, galaxies kept growing. A large galaxy like our Milky Way likely assembled from the amalgamation of many smaller progenitors over billions of years, each merger adding to its mass and mixing up its stars. Meanwhile, galaxies also grew by a quieter method, accretion of gas from their surroundings. Along the filaments of the cosmic web, tendrils of gas continued to funnel into galaxies, especially in the early universe. This fresh gas was fuel. It settled into rotating disks and kept star formation alive. In fact, even as major mergers built up the bulk of galaxies, a steady flow of intergalactic gas helped form extended disks and spiral structures. In galaxies that didn't undergo disruptive collisions for a long stretch, well, ordered disks had time to develop, the kind we see in majestic spiral galaxies. The Milky Way, for instance, has likely enjoyed a relatively quiet life for the past several billion years, allowing it to maintain its spiral disk and keep forming new stars at a modest rate by accreting gas. Galaxies also evolve internally. As generations of stars live and die within them, the galaxy's content changes. Early stars forged new elements and spread them out when they died, gradually enriching the galaxy's gas with heavier elements. This means later generations of stars, like our Sun, were born from material that had been recycled through previous stars, including elements crucial for planets and life. Over billions of years, the rate of star formation in the universe rose to a peak and then declined. That cosmic high noon, when galaxies were churning out stars at record pace, is long past. Many galaxies today are less active, having used up or lost much of their star-forming fuel. The environment around a galaxy plays a big role in how it evolves. A galaxy, floating relatively alone, might keep its gas and continue forming stars for a very long time. But a galaxy in a crowded cluster can have a much harsher life. As it plunges through the thin, hot plasma that fills galaxy clusters, its own gas can be stripped away like leaves torn off a moving car. With its gas gone, its star formation can slow to a halt, turning a once blue spiral into a gas, poor lenticular or elliptical over time. Also, frequent interactions in a cluster, small gravitational tugs from many neighbors, can stir up a galaxy's structure, making spiral arms disheveled or triggering periodic bursts of star formation until the gas is exhausted. Throughout cosmic time, mergers big and small continue to shape galaxies. Two sizable galaxies merging can transform their structures, often yielding an elliptical galaxy and perhaps fueling a quasar as their central black holes ignite. Minor mergers, where a big galaxy cannibalizes a smaller one, are common too. Our Milky Way is in the process of digesting several dwarf galaxies even now, their stars forming streams in our halo. Every such event adds stars to the larger galaxy and can jostle its structure slightly. Galactic evolution is thus a complex tapestry woven from smooth flows of gas, violent collisions, internal fireworks of star birth and death, and environmental influences from the cosmic neighborhood. Over 13.8 billion years, galaxies have grown from tiny embryonic fluctuations into the grand systems we see today. Many started as little more than glimmering irregular clumps. Some settled into stable rotating disks. Others underwent repeated smash-ups that left them as giant ellipticals. Some, especially smaller ones, remain irregular to this day, perhaps never having the chance to form a tidy structure. One intriguing aspect of galaxy evolution is the co-evolution of galaxies with their central black holes. Almost every large galaxy has a supermassive black hole in its core, and somehow these black holes grew in tandem with their galaxies. In the early universe, frequent mergers and copious gas likely fed the black holes, turning some into blazing quasars. There's a curious correlation today. The mass of a galaxy's central black hole closely relates to the mass of the galaxy's bulge of stars, hinting that galaxies and black holes regulated each other's growth. It's a bit of a chicken or egg problem. Did big galaxies form first and then their black holes? Or did black holes form and help shape galaxies? But evidence suggests an intricate feedback dance. For example, a quasar can unleash so much energy that it blows gas out of the host galaxy, quenching further star formation for a time. Thus, the evolution of a galaxy is tied not only to external events, but also to the sometimes fierce influence of its own central engine. From the primordial gas collapsing into the first star clusters, to the grand collisions that built up cluster giants, galaxy evolution spans the entire history of the universe. It's still ongoing. Even now, galaxies continue to interact and grow. Our local group of galaxies is quiet at the moment, but the Milky Way and Andromeda are drifting inexorably closer and will merge billions of years from now,
reshaping into a new, larger galaxy. Eventually, as eons pass, galaxies will use up much of their gas and star formation will slow to a trickle. The night skies of the far future may be dominated by aging red stars and fading galaxies. But for now, in this epoch, galaxies of all types still populate the cosmos, from lively spirals to sleepy ellipticals, each a product of the rich, evolutionary journey that took it from the aftermath of the Big Bang to the form we observe today.
When galaxies collide, cosmic encounters and mergers. Galaxies are not static, isolated islands. They often interact and sometimes collide in a slow motion dance governed by gravity. Imagine two enormous cities drifting toward each other over eons. As the galaxies draw near, their mutual gravity stretches and warps them. Long tidal tails of stars are drawn out, and great arcs of gas are flung into intergalactic space. If we could watch this unfold, we'd see the two galaxies distort like taffy being pulled, perhaps looping around each other once or twice. Over hundreds of millions of years, they may sway back and forth in a gravitational embrace before eventually merging into one. Despite the word collision, individual stars almost never hit head-on during these encounters. The distances between stars are just too vast. The galaxies pass through each other like ghosts, but gravitational forces wreak havoc on their structures. The delicate spiral arms of a spiral galaxy can be torn apart or twisted into new shapes. In some cases, a smaller galaxy plunging through a larger one can spark a graceful ring galaxy like a ripple in a pond. In other cases, two spiral galaxies entangle, throwing out twin tidal tails of stars. The colliding antennae galaxies are a beautiful real example, their long filaments of stars and gas arcing out like insect antennae as their disks intersect. Within the antennae, telescopes see countless young star clusters ignited by the collision. It's a glimpse of what our own Milky Way might undergo in its future encounters. One of the most dramatic effects of a galactic collision is on the galaxy's gas. When galaxies collide, their vast clouds of gas slam into each other. Unlike stars, gas clouds do collide, compressing violently. This compression can ignite a starburst, a sudden surge of star formation. In the aftermath of a collision, the merging galaxies may glow with the light of countless newborn stars, a fireworks show that can outshine a normal galaxy. The antennae galaxies, for instance, are experiencing such a burst of star birth as they merge, with brilliant clusters of young stars lighting up the wreckage. In addition, as the two galaxies coalesce, their central supermassive black holes will eventually spiral toward each other and merge as well, potentially releasing a burst of gravitational waves. Over time, the result of a major merger is often a single, more massive galaxy. Two spiral galaxies colliding will likely settle into an elliptical galaxy, their orderly disks destroyed, their gas largely converted into stars or expelled, leaving a big ball of stars. The chaos of the merger tends to randomize the orbits of stars, which is why the end product has that puffy, elliptical shape rather than a flat disk. We see evidence of past mergers in some galaxies today. Giant ellipticals often have faint shells or ripple patterns of stars around them, the ghostly remains of smaller galaxies they absorbed. Our own Milky Way shows signs of past minor mergers too. Streams of stars in the halo mark where dwarf galaxies were torn apart and assimilated. Even small interactions can leave lasting impressions. A flyby of a smaller galaxy might induce spiral arms or bars in a larger galaxy, or cause a burst of star formation by jostling its gas. Galaxies can also cannibalize their companions. A big galaxy like the Milky Way can slowly consume a small satellite galaxy, pulling it apart over billions of years. In fact, the Milky Way is doing this right now to at least 2 known dwarfs, their stars being strung out into lengthy loops around our galaxy as they are assimilated. These minor mergers are gentler than a head-on collision of equals, but they still contribute to a galaxy's growth and can subtly disturb its structure. One collision in particular stands out to us because it lies in our future: the anticipated encounter between the Milky Way and the Andromeda Galaxy. Andromeda, currently about 2.5 million light-years away, is on a slow collision course with us, due to meet our Milky Way in about 4 billion years. Though that sounds comfortably far off, in cosmic terms, both galaxies are essentially fated to merge. What will this titanic meeting be like? As Andromeda nears, by about 3.75 billion years from now, it will loom huge in Earth's sky, likely visible in daytime, a swirling disk of billions of stars that begins to distort the Milky Way with its tidal pull. Eventually, the disks of the two galaxies will begin to interpenetrate. Stars from Andromeda and stars from the Milky Way will sweep past one another like intermingling bees. The night sky would become a twisted, kaleidoscopic panorama of disrupted star streams, nebula set alight by shockwaves, and new star clusters forming in droves. According to simulations, the Milky Way and Andromeda will likely pass through each other once, then maybe swing around and merge fully by around 6 or 7 billion years from now. During the interaction, our solar system is unlikely to collide with another star, but its orbit around the Milky Way could be drastically altered. It might be flung into a new region of the merged galaxy, perhaps much farther from the core than it is today. By the end of the merger, the orderly spiral patterns of both galaxies will be gone. Instead, we would find ourselves in a large, amorphous, elliptical galaxy, sometimes nicknamed Milkomeda. The merged galaxy will have a new identity, containing most of the stars from both the Milky Way and Andromeda, now sharing a common cloud of stars. Though this sounds catastrophic, it's worth noting that for any beings on individual stars, the chance of a direct stellar collision or disruption is very low. They might hardly notice the gravitational collision aside from a gradually changing night sky. The real violence is in the gas and the overall structure, and indeed, if humanity's far descendants are around, they might witness a sky ablaze with more stars and nebulae than ever as the collision triggers star formation. It would be an awe-inspiring spectacle. Galactic collisions are a crucial part of the life cycle of galaxies. Through them, galaxies grow and change form. They can rejuvenate a galaxy by kick, starting starbirth, or they can quench a galaxy by using up and ejecting star, forming fuel. They create some of the most stunning vistas in the universe, luminous tails, rings, and collisional remnants that we observe with our telescopes as snapshots of different stages of this cosmic dance. In the grand scheme, collisions are also how we got from the small primitive galaxies of the early universe to the large galaxies of today. The Milky Way. Andromeda collision will be just one of countless such events that have happened throughout cosmic history and will continue to happen as time marches on. Even as the universe expands and distant galaxies recede from each other, gravitationally bound groups like our local group will eventually coalesce. The end result, far in the future, might be giant combined galaxies, each isolated in an ever-expanding void. For now, we can look at interacting galaxies elsewhere in the cosmos to understand our own galaxy's fate and the dramatic transformations collisions bring. Next, we zoom in on one of the most beautiful outcomes of galactic evolution, the process by which galaxies give birth to new stars. Whether in the wake of collisions or in the calm spiral arms, star formation is the ongoing heartbeat of a galaxy, and it's to these cosmic nurseries that we turn. The alchemy of stars, galactic nurseries, and stellar birth. Every star, including our sun, was born in a cosmic nursery, a great cloud of gas and dust within a galaxy. These nurseries, known as molecular clouds, are cold, dense patches of the interstellar medium. A typical molecular cloud might contain thousands to millions of times the mass of the sun in gas, spread over dozens or hundreds of light years. Within these dark, frigid clouds,
gravity quietly begins its work. Small random density enhancements grow as gas clumps together. If a region becomes dense enough, its own gravity causes it to collapse inward. As it collapses, it fragments into smaller pockets, like a lump of dough breaking into pieces, each destined to form one or a few stars. Deep inside one of these collapsing clumps, the material compresses and heats up. A protostar takes shape, a hot, dense core of gas that isn't a true star yet, but is on its way. As the protostar gains mass from the infalling cloud, its core grows hotter and more pressurized. Eventually, when the temperature and pressure skyrocket enough, hydrogen nuclei begin to fuse into helium. This ignites the nuclear fire at the protostar's center E, and a star is born. The newfound star's radiation and stellar winds then push away the remaining shroud of gas around it, often creating a beautiful glowing nebula as the gas is ionized. What was once an opaque, dark cloud now becomes a stellar nursery, lit up by its offspring. Stars tend to be born in batches. A single collapsing cloud can give birth to a whole cluster of stars, some hefty and bright, some smaller and dim. For example, peer into the Orion Nebula, a stellar nursery about 1/300 light years away. You'll see a glowing cavern of gas and dust lit by a clutch of brilliant newborn stars. Within that nebula, dozens more protostars hide in cocoons, still gathering mass. It's a snapshot of starbirth in action, a miniature version of the process unfolding countless times across our galaxy. The trapezium cluster of massive young stars at Orion's heart is carving a cavity in the cloud with intense ultraviolet light and stellar winds. Within such clusters, the most massive stars blaze to life first. Their intense radiation and powerful winds carve cavities in the cloud and can trigger further collapse in nearby parts of the cloud. In this way, massive stars can act both as catalysts and inhibitors for the next generation of stars. They are short-lived, however, living only a few million years. And when they die as supernovae, they send shockwaves through the cloud that can compress it in places and disperse it in others. In a spiral galaxy, these processes are not happening randomly everywhere, but often concentrated in the spiral arms. The spiral arms are like traffic jams in the galaxy's disk. They are regions where gas clouds get squeezed as they orbit the galactic center. When a molecular cloud enters the denser environment of an arm, it can trigger collapse and star formation. As a result, we see bright young star clusters and HII regions lining the spiral arms, marking the locations of recent star birth. These newborn stars, especially the hot blue ones, shine brilliantly but burn out quickly, so they don't drift far from their birthplaces. Hence, the arms remain defined by these ongoing nurseries. Meanwhile, older stars have had time to move away, so between the arms we mostly find middle-aged and old stars. Different galaxies have different personalities in terms of star formation. Our Milky Way currently forms only a few solar masses worth of new stars each year, quietly and steadily. In contrast, some galaxies, especially those experiencing interactions or mergers, can undergo starbursts, where dozens or even hundreds of solar masses of stars form per year. These starburst galaxies are ablaze with massive young stars, and they radiate strongly in infrared as dust in the galaxies is heated by the intense stellar newborns. Irregular dwarf galaxies can also have phases of rapid star formation, often triggered by a brush with a larger neighbor or by a fresh influx of gas. On the flip side, galaxies that have lost or exhausted their gas have virtually no new stars forming. Their stellar populations are aging without rejuvenation. Star formation is a feedback loop within a galaxy. When stars form, especially massive ones, they alter their environment dramatically. The combined effect of many massive stars in a region, through stellar winds, supernova explosions, and radiation, can create superbubbles that blow holes in the galactic gas disk, venting material out into the halo. Some of that gas may cool and rain back down to the disk later, potentially forming new clouds. Or it may escape the galaxy entirely if driven hard enough, especially in a starburst or quasar phase, an event that can effectively shut down future star formation by removing fuel. In moderate amounts, though, feedback from stars helps to regulate the pace of star formation, preventing the galaxy from turning all its gas into stars at once. Over the life of a galaxy, star formation acts as a clock and a forge. It's a clock because the rate at which gas turns into stars will determine how long a galaxy's star-forming era lasts. A galaxy with a slow rate can keep making stars for tens of billions of years, while one with a rapid rate might use up its gas in only a few billion. It's a forge because each generation of stars produces heavier elements in their cores and in supernovae. Those elements get mixed into the galactic gas reservoir. Thus, the composition of the gas slowly changes. The galaxy becomes more metal-rich over time, which influences things like planet formation around new stars. In fact, our own existence is tied to this cosmic alchemy. The carbon in our cells, the calcium in our bones, the iron in our blood were all formed in previous generations of stars and scattered into the interstellar medium, eventually coalescing into the Sun and Earth. Galaxies, by forming stars, gradually enrich the cosmos with the ingredients for planets and life. Within galaxies, different environments yield different kinds of star formation. In the dense heart of a starburst or the core of a merging galaxy, star formation might be so rampant that hundreds of thousands of massive stars form in a short time, leading to an outbreak of supernovae like a cosmic storm. In the quiet outskirts of a spiral galaxy, small clouds might occasionally birth only low, mass stars, faint red dwarfs that will live for trillions of years. Some galaxies, like large spirals, have a mix of environments, busy spiral arms and calmer inter-arm spaces, creating a balance of star formation across various scales. Other galaxies, like ellipticals, are essentially retired, containing gas that's too hot or diffuse to collapse, so star formation is dormant. From a bird's eye perspective of a galaxy, you would see star formation as twinkling patches of light. Here, a cluster of blue newborn stars. There a glowing nebula around an emerging cluster. If you could watch in accelerated time, you'd see clouds collapse and ignite, and perhaps, after a few million years, see bubbles and blasts from supernovae shaping the surroundings. It's an endless cycle. Galaxies are constantly converting some portion of their gas into stars, which then live out their lives and return some material back to the galaxy when they die. This ongoing stellar production line is the engine that keeps a galaxy visible and vibrant. It is literally the act of galaxy building, assembling new stellar components that, for a time, light up the galaxy from within. In sum, star formation is the beating heart of a galaxy's evolution. As long as a galaxy has gas, it can give birth to stars, and thus continue the cosmic story, lighting up the darkness, forging new elements, and providing the raw material for planets and potentially life. Next, we explore an enigmatic ingredient that heavily influences all these processes, yet reveals itself only through gravity: the dark matter that surrounds galaxies and shapes their fate. The hidden mass, dark matter's grip on galaxies. Galaxies are not just made of stars and gas. They are enveloped by something immense and invisible that we call dark matter. This dark matter doesn't emit light, doesn't shine or obscure like dust. It interacts with ordinary matter only through gravity, yet it profoundly influences the behavior and fate of galaxies. In fact, most of the mass in a typical galaxy is dark matter, outweighing the visible stars and gas by a factor of 5 or more. It's the hidden scaffold that holds galaxies together and connects them in the cosmic web. The first hints of dark matter's presence came from observations that didn't add up. In the 1930s, the eccentric Swiss astronomer Fritz Zwicky first proposed the existence of dark matter in 1933 after observing the motions of galaxies in the Coma cluster. He calculated that the visible galaxies didn't have nearly enough gravity to hold the cluster together. Zwicky, in his blunt style, invoked a mysterious dunkel materia, or dark matter, to explain the discrepancy. His idea was ahead of its time. It was largely dismissed or forgotten for decades. Later, in the 1970s, astronomer Vera Rubin and her colleague Kent Ford made a landmark discovery after many meticulous nights at the telescope. They measured the rotation curves of spiral galaxies, essentially how fast stars and gas orbit at different distances from the galaxy's center. In a whirlpool like the solar system, we expect objects farther out to orbit more slowly because the gravity of the central mass gets weaker with distance. But Rubin found, to her astonishment, that in spiral galaxy after galaxy, the stars in the outer disks were orbiting just as fast as stars near the center. The rotation curves were flat. The expected drop off never came.
This was a startling clue. If the only mass in the galaxy were the stars, gas, and dust we can see, the outer stars should not have enough gravitational pull to stay bound at such high speeds. They should drift away into space. The fact that they remain orbiting at high speed means there must be a lot of unseen mass extending well beyond the visible edge of the galaxy, creating a strong gravitational pull. The simplest explanation: an extensive halo of dark matter envelops the galaxy. This halo, roughly spherical, contains most of the galaxy's mass, though it emits no light. The stars in the outer disk are effectively orbiting within this massive invisible halo, which keeps them tethered.
Dark matter halos are thought to extend far beyond the luminous parts of galaxies. For example, while the Milky Way's visible disk is about 100,000 light-years across, its dark matter halo may span 600,000 light-years or more. If we could see it, our galaxy's halo might look like a giant sphere, much larger than the Milky Way's starlit spiral, gently fading into the intergalactic medium. Every galaxy sits within such a halo, from large spirals to tiny dwarfs. In small dwarf galaxies, in fact, the dark matter's grip is often even more dominant. These little galaxies might have relatively few stars, but still plenty of dark matter, which is the only thing holding their sparse stars together. Dark matter's influence goes beyond keeping galaxies intact. It played a crucial role in galaxy formation. As described earlier, dark matter clumped into filaments and halos in the early universe, and ordinary gas fell into those gravitational wells to form galaxies. The cosmic web of large-scale structure, the immense network of galaxy clusters and filaments spanning hundreds of millions of light-years, is essentially the imprint of dark matter's distribution, with galaxies lighting up the densest spots. Without dark matter, our theories struggle to explain how the universe's structure could have formed as quickly as it did. Dark matter, being pressure, less unable to clump early, seeded galaxy formation long before normal matter could do so. Within individual galaxies, dark matter also affects their dynamics and evolution. The presence of a massive halo can stabilize a rotating disk against certain instabilities. It provides an extra gravitational well that can funnel gas towards the center or help sustain spiral density waves. When galaxies collide and merge, their dark matter halos pass through each other and overlap, adding together to form an even bigger halo around the new merged galaxy. In cluster environments, the combined dark matter of the cluster forms a deep gravitational well that can trap galaxies and super-hot gas. One of the most striking pieces of evidence for dark matter comes from images of gravitational lensing. According to Einstein's general relativity, mass bends space and thus bends light. In some massive clusters of galaxies, we see distorted, smeared images of far background galaxies, as if viewed through a funhouse mirror. These distortions allow astronomers to map the mass in the cluster. The maps show that there's far more mass than what we can see in stars and gas. A famous example is the Bullet Cluster, two colliding clusters of galaxies. In the aftermath, the X-ray emitting hot gas from each cluster was slowed and left behind at the collision center, whereas the galaxies flew on. Gravitational lensing revealed that the main mass of the clusters moved ahead with the galaxies, not with the gas, implying that the mass is dominated by something that did not collide and slow down like the gas did. This observation is a stunning confirmation that dark matter is a real physical component, separate from normal gas. Even with all this evidence, what dark matter actually is remains one of the greatest mysteries in science. We know it's there. We map its distribution. We see its gravitational effects everywhere, from the rotation of tiny dwarf galaxies to the expansion of the universe as a whole. The leading idea is that dark matter consists of some new kind of subatomic particle that doesn't interact with light, perhaps a type of particle left over from the Big Bang that swarms around galaxies. Physicists have given these hypothetical particles names like WIMPs or axions. Huge experiments deep underground and in space are attempting to detect a stray dark matter particle, and powerful colliders like the Large Hadron Collider search for hints of them. So far, dark matter particles have eluded direct detection, adding to their mystique. What we do know is that without dark matter, galaxies as we understand them wouldn't exist. Galaxies would not have formed in the same way, and those that did might not hold together. Dark matter's gravity is the glue keeping the grand design of a spiral galaxy intact and the engine that assembled galaxies in the first place. It ties entire clusters of galaxies into bound communities and delineates the cosmic web on the largest scales. In essence, dark matter is the invisible stage on which the luminous drama of stars and galaxies unfolds. We find ourselves living inside this invisible halo, unaware of its particles as they stream through us, yet deeply dependent on their gravitational presence for our very existence in a galaxy. Understanding dark matter is crucial to fully knowing galaxies, their rotation, their shape, their past, and their future. As our story of galaxies continues, we turn our attention back to the visible centers of these systems, in particular to the monsters lurking there. In the cores of galaxies, including our own, lie supermassive black holes that, when awakened, can blaze forth as active galactic nuclei and quasars, outshining entire galaxies. These extreme objects are another key piece of the galactic puzzle. Galactic beacons, quasars, and active nuclei. In the heart of almost every large galaxy lies a supermassive black hole, a gravitational titan millions or billions of times the mass of the Sun. Most of the time, these black holes are quiet, lurking in the darkness as stars and gas orbit innocently around them. But when a black hole feeds, a galaxy can transform. Matter swirling into a hungry black hole releases astonishing energy, enough to outshine the entire galaxy. The nucleus of the galaxy blazes with light, and we call it an active galactic nucleus. When an AGN is extremely luminous, especially seen in the distant universe, we often use the term quasar. A quasar is essentially a hyperactive galactic core E, a supermassive black hole gorging on infalling gas and shining like a beacon across the cosmos. How does a black hole, which by itself emits no light, produce such brilliance? The key is the accretion disk, a swirling disk of gas and dust that forms around the black hole as material falls in. As matter spirals inward, immense gravitational and frictional forces heat the disk to incredible temperatures, millions of degrees. The disk begins to glow fiercely in X-rays, ultraviolet, and visible light. Gas closer in moves at relativistic speeds, magnetic fields twist through the disk, and often the black holes spin and magnetic forces channel some of the inflowing material into twin jets that shoot out along the black hole's poles. These jets are streams of charged particles accelerated to nearly the speed of light, blasting out of the galaxy's core into space. They can extend thousands or even millions of light years, creating radio, emitting lobes far outside the galaxy. To an observer from afar, a galaxy with an active nucleus might appear as a bright star, like point at its center, or even completely outshine the galaxy's entire starlight. Quasars in the distant universe appear as brilliant beacons on the sky, some of the brightest individual objects known. For instance, a typical quasar can emit hundreds or thousands of times more light than a normal galaxy containing 100 billion stars. And all that energy comes from a region no larger than our solar system, the area right around the black hole. It's as if a flashlight the size of a pinhead outshone a lighthouse. That's the power of a feeding supermassive black hole. Quasars were first identified in the 1960s as puzzling sources of radio waves and faint, star-like optical counterparts with strange emission lines. When astronomer Martin Schmidt realized those lines were highly redshifted hydrogen, it meant these objects were incredibly distant, yet astonishingly bright. This was the first clue that quasars were not stars in our own galaxy, but something far more powerful in the distant universe. We now know thousands of quasars, and we interpret them as galaxies in an active phase. Their central black holes are accreting matter at a high rate. Quasars were more common in the early universe, which makes sense. Back then, galaxies had more gas in their centers and were colliding more frequently, providing ample fuel for black holes. Many quasars lived during that cosmic era when galaxies were growing and merging. Today, with less fuel available, most big galaxies have quiescent black holes. Our Milky Way's central black hole, for example, is currently a feeble glimmer by quasar standards. It occasionally snaps up a passing chunk of material, producing a flicker of X-rays, but nothing like a continuous blaze. Active galactic nuclei come in a menagerie of types: quasars, blazars, Seyfert galaxies, radio galaxies, which largely reflect different viewing angles and power levels of the same basic phenomenon. If we look directly down the barrel of a jet, we see a blazar. If the active nucleus is powerful, but we see it at an angle where the galaxy's dust obscures some light, we might categorize it as a radio galaxy or a type of Seyfert galaxy. But all these are AGNs, central engines powered by accretion onto supermassive black holes. The effects of a quasar or AGN on its host galaxy are profound. The radiation and winds from the active nucleus can blast apart or heat the gas in the galaxy's core. A vigorous quasar can effectively quench star formation in its host by blowing away or heating the cold gas. This means that a galaxy's active heart can govern its own growth, a kind of self-regulating mechanism. If too much gas piles into the center, the black hole lights up, the quasar blows out gas, and the galaxy's star, forming future, is altered. This feedback might explain why we observe the tight correlation between black hole mass and the bulge mass of galaxies. They grew in tandem, each affecting the other. Observationally, an active galaxy can look quite spectacular. Some galaxies have bright cores and jet structures visible in radio or optical images. In images from Hubble or James Webb, we sometimes see quasars with faint galactic hosts around them, or pairs of interacting galaxies where one nucleus is lit up, possibly triggered by the interaction. When we peer into the distant universe, almost every speck of light in the Hubble ultra-deep field that isn't a star in our Milky Way is a quasar shining from an era long ago. The existence of quasars tells us that galaxies and their black holes are intimately connected. A galaxy might spend a small fraction of its life as a quasar, but during that time it can have an outsized influence on its surroundings and be visible clear across the universe. In a sense, quasars are cosmic lighthouses, marking where massive black holes dine. They allow us to study galaxies in the making, as many quasars are seen in young, formative galaxies undergoing collisions or rapid growth. They also serve as backlights. We can study the gas in the space between galaxies by looking at how quasar light filters through it. Our Milky Way's black hole might one day gulp enough material to become more active, though it likely would never rival the brightest quasars from the universe's youth. Still, even a modest AGN can produce spectacular phenomena like X-ray flares or relativistic jets. The center of our galaxy shows evidence of past active episodes, gigantic bubble structures emanating from the core, perhaps from an AGN flare a few million years ago. In the grand tapestry of galactic life, quasars represent a youthful exuberance, a time when a galaxy's central engine can dominate its light output. They are a phase that many galaxies likely went through. Today, by studying both gentle galaxies and those with raging quasars, we get a complete picture of galactic evolution. We see a galaxy's quiet, star, forming suburbs, and also its volatile, energetic core when it turns on. With the phenomenon of AGN understood, we can now appreciate that a galaxy is not just a collection of stars drifting passively. It has a central heart that can beat furiously when fed. Having explored the brilliant hearts of galaxies, we now step back out to consider something smaller, yet still crucial to the galactic story: the dwarf galaxies that swarm around larger ones and fill the universe. These diminutive galaxies may be tiny, but they carry clues about how galaxies form and about the mysterious dark matter, making them far more important than their size suggests. Little brothers, dwarf galaxies and galactic satellites. Surrounding every large galaxy are smaller satellite galaxies, dwarf galaxies, the diminutive companions that populate the universe in huge numbers. Dwarf galaxies are tiny by galactic standards, perhaps only a few thousand light years across or less, containing as few as a few million stars. They come in various flavors. Some are irregular clumps with ongoing star formation. Others are diffuse spheroids of old stars. Though they may seem insignificant next to a giant spiral or elliptical, these little galaxies play an outsized role in the story of cosmic evolution. In our own cosmic neighborhood, the Milky Way has dozens of known dwarf satellites. The two most famous are the large and small Magellanic Clouds, irregular dwarf galaxies visible to the naked eye in the southern hemisphere. These clouds are actively forming stars, with visible nebulae like the Tarantula Nebula in the Large Cloud, a colossal star, birth region. They orbit our Milky Way and are in the process of being gradually disrupted. A stream of gas, the Magellanic Stream, stretches behind them, torn off by our galaxy's gravity and the ram pressure of halo gas. In a few billion years, the Magellanic Clouds will likely merge into the Milky Way, adding their stars to our own. Besides these prominent examples, the Milky Way is encircled by many dwarf spheroidal galaxies, much smaller, fainter objects like Sagittarius, Draco, Ursa Minor, and Fornax. These tend to have little to no gas and consist mostly of ancient, faint stars. They often appear as just a sparse scattering of stars, detectable only with long exposures on large telescopes. The Sagittarius dwarf is actually in the process of being devoured by the Milky Way right now. It has been stretched into a long stream of stars, wrapping around our galaxy. Over time, its stars will assimilate into the Milky Way's halo. Each of these tiny galaxies is like a fossil record of the early universe. Many of them formed their stars more than 10 billion years ago and haven't done much since, preserving a snapshot of conditions shortly after galaxies began to form. Dwarf galaxies are incredibly valuable to astronomers as laboratories for dark matter and galaxy formation. They are the most dark matter-dominated galaxies known. In some ultra-faint dwarf galaxies, the few thousand stars move under the influence of a dark matter halo that outweighs them by hundreds or thousands of times. One extreme case is Segway 1, a diminutive Milky Way satellite so faint it has only a few hundred stars, yet they are held together by a blob of dark matter roughly 600,000 times the Sun's mass. That means Segway 1's mass is almost entirely dark matter, with a barely detectable glimmer of starlight. measurements of star motions in tiny galaxies like Segway 1 or Triangulum 2 suggest that these systems might have up to 1,000 times more mass in dark matter than in stars. It's as if each faint dwarf is mostly a ball of dark matter with a sprinkling of stars. This makes them excellent testbeds for dark matter theories. How does dark matter cluster on small scales? Are the number of dwarf galaxies we see consistent with predictions from cosmological models? At first, there was a missing satellite problem. Computer simulations of cosmic structure predicted that a Milky Way-sized halo should have hundreds of smaller sub-halos orbiting it, potential dwarf galaxies. Yet for a long time we had observed only a few dozen around the Milky Way. Where were the rest? In the past 2 decades, however, new ultra-faint dwarf galaxies have been discovered in droves. The count of Milky Way satellites has climbed substantially, and we now suspect many more await detection, lurking in the shadows with extremely few stars. It seems that many dark matter sub-halos did form, but most of them failed to produce many stars, likely because the cosmic reionization heated and stripped gas from the smallest protogalaxies. Star formation in those puny halos was stifled, rendering them effectively dark. The ones we do see are the slightly bigger or luckier halos that manage to form stars despite these harsh conditions. The dwarfs that do shine provide crucial checks on our cosmological models. Their distribution around the Milky Way, their orbits, and their internal properties all carry information about how our galaxy were assembled. For instance, studies find that many of the Milky Way's dwarf satellites lie in a somewhat flattened arrangement, a feature still debated and potentially telling us something about past interactions or the filamentary nature of how they were acquired. The star formation histories of dwarfs also vary. Some, like the Magellanic Clouds, still form stars today. Others, like the dwarf spheroidals, formed most of their stars early and then stopped. Environment is a factor. Dwarfs near a big galaxy often lose their gas and thus cease making new stars, while isolated dwarfs farther away can retain gas longer. Dwarf galaxies are thought to be the building blocks of larger galaxies in the hierarchical model of cosmology. Over billions of years, small protogalaxies merged to build big ones. Essentially, today's large galaxies are the result of many past dwarf galaxy collisions and mergers. In our Milky Way's halo, astronomers identify remnants of several dwarf mergers beyond just Sagittarius. These show up as stellar streams or distinct groups of stars with common origins. The globular clusters orbiting our galaxy may include some that were originally brought in by dwarfs. In Andromeda, our nearest large neighbor, the halo is even more populated with substructures and streams, evidence of a rich history of consuming smaller companions. Dwarfs also affect their parent galaxies in subtle ways. A satellite can tug on the primary galaxy via gravity. For example, the Large Magellanic Cloud is massive enough that it's pulling on our galaxy, causing both to move toward their common center of mass. Interactions between a dwarf and a large galaxy can create disturbances. The Milky Way's disk has ripples and warps, possibly induced by past encounters with satellites. And when a dwarf with fresh gas orbits a big galaxy, it can funnel gas into the big galaxy's halo, which may later rain down and fuel future star formation in the main galaxy. Thus, dwarfs can be providers of material, not just victims. They might extend the star, forming life of a big galaxy by donating gas during their infall. Because of their small size, dwarf galaxies also highlight the thresholds and extremes of galaxy formation. They exist in regimes where a single burst of star formation can exhaust their supply or blow out what's left. Some dwarfs show evidence of one ancient burst and then long quiescence. Others, in isolation, might have sporadic bursts separated by many millions of years as gas slowly pools in again. Some tiny galaxies may have been completely stunted by the ionizing glare of the first stars and quasars during reionization, never forming many stars at all. They remind us that not all galaxies are the continuously rotating, long-lived star factories like the Milky Way. Some are stop and go, some are one and done, and everything in between. In summary, dwarf galaxies may be small, but they are crucial pieces of the cosmic puzzle. They were the first galaxies to form, the building blocks that merged into larger ones. They are the most common galaxies by number. They are reservoirs of dark matter, offering evidence for its behavior on small scales. And as satellites, they are constantly interacting with larger galaxies, being pulled apart, contributing gas and stars, and generally complicating the life of their big hosts. In their diminutive form, dwarfs carry outsized importance for understanding gravity, dark matter, and the history of galaxy assembly. Having explored these miniature galaxies, we now widen our perspective to the enormous patterns that galaxies themselves form on the grandest scales. Just as stars gather into galaxies, galaxies congregate into clusters, superclusters, and filaments in a vast cosmic web. It's time to venture into the large-scale structure of the universe, the architecture of galaxies on cosmic scales.
The cosmic web, clusters, superclusters, and filaments. Galaxies, including the Milky Way, are not scattered randomly through space. They often gather in larger structures bound by gravity. On the first rung of this cosmic ladder are galaxy groups. A galaxy group generally holds a few dozen or fewer galaxies. The Milky Way and Andromeda, along with the dozens of dwarf galaxies orbiting them, form the local group, a collection of more than 50 galaxies spanning about 10 million light-years. Our local group is a typical small cluster. It has two dominant spirals, a third spiral, and many dwarfs. The galaxies in the local group orbit their common center of gravity and are bound together. Step up in scale, and we find galaxy clusters. These are much larger assemblies, containing anywhere from hundreds to thousands of galaxies, all bound in a single gravitational swarm. Galaxy clusters are among the most massive coherent structures in the universe. A good example is the Virgo cluster, the nearest sizable cluster, roughly 50 million light-years away in the direction of the constellation Virgo. It holds over 1,000 galaxies in a volume a few million light-years across. The cluster's core is crowded with elliptical galaxies, including a giant central galaxy sitting at the center, feasting on smaller galaxies that venture too close. Clusters like Virgo are permeated by a hot X-ray, emitting gas that fills the space between galaxies. This intracluster gas actually outweighs all the stars in the cluster, and dark matter outweighs both. Clusters are dark matter, dominated just like galaxies, but on a larger scale. The galaxies in a cluster move at hundreds or even over 1,000 kilometers per second, ricocheting through the cluster's deep gravitational well. Clusters themselves aren't isolated. They often lie in larger complexes called superclusters. A supercluster is essentially a cluster of clusters, an extended grouping of galaxies, groups, and clusters spanning perhaps a few 100 million light-years. Our local group, for instance, is on the outskirts of the Virgo supercluster, which contains the Virgo cluster and dozens of other groups and clusters in our corner of the universe. In recent years, astronomers have realized that what we used to call the Virgo supercluster is part of an even larger complex named Laniakea, a Hawaiian word meaning immense heaven. The Laniakea supercluster, as mapped by the flow of galaxies, includes the Virgo cluster, the Hydra, Centaurus supercluster, and other clusters, all linked by gravity. It stretches over 500 million light-years and contains the mass of perhaps 100,000 galaxies. At the center of Laniakea is a gravitational focal point dubbed the Great Attractor, a region of space causing a peculiar motion of our local group and others toward it. This Great Attractor's pull is part of the evidence of Laniakea's extent. Connecting these clusters and superclusters are the filaments, long strings of galaxies and galaxy clusters, tens to hundreds of millions of light, years long, but relatively thin. Between the filaments lie voids, enormous regions with very few galaxies, sometimes tens of millions of light, years across where only a handful of galaxies dwell. One famous void, the Boötes void, is about 330 million light years in diameter and contains very little. It's been whimsically described as a spherical space with nothing in it, though in reality there are a few galaxies scattered within. The contrast between filaments and voids gives the universe a kind of foamy texture. Some filaments can join together into sheet, like structures or walls. For example, the Sloan Great Wall, identified in large galaxy surveys, is a massive thread of galaxies and clusters, about 1.5 billion light years long, among the largest structures ever observed. The cosmic web's appearance is often compared to a sponge or foamy bubbles, concentrations of matter surrounding vast empty voids, or even to the brain's neural networks on a cosmic scale. This arrangement, clusters, superclusters, filaments, and voids, is what we call the cosmic web. It formed from the same primordial fluctuations we discussed earlier, amplified by gravity over cosmic time. Dark matter played the key role. It clumped into filaments early, and ordinary matter followed, flowing into those gravitational channels to form galaxies. The result is that on the grandest scales, matter in the universe is arranged in twisting, thread-like structures with immense voids in between. When we run large computer simulations of the universe, starting from the initial conditions of the Big Bang and letting gravity draw matter together, a filamentary pattern naturally emerges. The simulation's output, when compared to maps of real galaxies from surveys like the Sloan Digital Sky Survey, is strikingly similar. It's one of the triumphs of modern cosmology. The cosmic web we observe is exactly what our theories predict given dark matter and the expanding universe. To give a sense of scale, an individual galaxy might be 100,000 light years across, a cluster 10 million, a supercluster 200 million, the distance between major superclusters on the order of 1 billion light years. The observable universe is about 93 billion light years in diameter. On those largest scales, the cosmic web starts to blend into homogeneity. An extremely large cube of the universe would contain a statistically even mix of galaxies and voids. But up to those enormous scales, the web is evident. It's breathtaking to realize that the Milky Way, with all its hundreds of billions of stars, is but a single point on the vast cosmic web, a node in a structure so immense it defies full comprehension. In a thought experiment, imagine pulling back your vantage point. Zoom out from our solar system, past the Milky Way's disk, until our whole galaxy is just a glowing spiral among others. Zoom further, and the Milky Way and its neighbors blend into the local group, a small cluster of galaxies. Pull back more, the local group becomes just one clump in the Virgo cluster. Further still, the Virgo cluster and adjacent groups merge into the Laniakea supercluster, a great flowing concentration of matter. Finally, as you zoom to a view hundreds of millions of light years across, the superclusters themselves line up as filaments, the cosmic web revealed in its entirety, galaxies like grains of dust, tracing the grand design of gravity. This mental journey underscores how nested our existence is within ever grander systems. We live within this web. Our Milky Way, Andromeda, and neighbors float together in the local group, which is being gently pulled as part of the Virgo Laniakea supercluster along a filament towards the Virgo cluster. In far, far future billions of years, that journey might bring our remnants into Virgo's embrace. When we peer out at the night sky, the stars we see with the naked eye all belong to our own galaxy, but the faint smudges we see through telescopes are all part of this grand structure. For instance, the Coma cluster of galaxies appears as a dim patch in the constellation Coma Berenices, but it is the heart of a rich filament connected to other clusters.
The Shapley supercluster, one of the most massive supercluster concentrations known, is another knot in the web, observable in southern skies. The cosmic web is not just a backdrop, it influences how galaxies evolve. Galaxies in clusters are different from those alone in the field. They tend to be redder and gas-poor, partly due to interactions and the hot cluster environment stripping their gas. Galaxies riding along thin filaments can funnel towards clusters, often getting processed by smaller group environments before entering a cluster. Thus, a galaxy's larger scale environment plays a role in its story, illustrating the adage, location, 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 on a cosmic scale. It's remarkable to think that barely 100 years have passed since we even confirmed galaxies outside the Milky Way. Now, with our arsenal of observations and simulations, we have mapped the architecture of the universe on the largest scales. We have, in essence, discovered the blueprint of creation's vast cosmic web. Having charted out this grand design, we turn to some of the most puzzling denizens of this landscape, galaxies that challenge our definitions, those that are extremely diffuse or even seemingly made mostly of dark matter with hardly any stars. These ultra, diffuse and dark galaxies push the boundaries of what a galaxy can be, and exploring them will deepen our insight into the unseen components of the universe. Ghostly galaxies, ultra, diffuse and dark galaxies. Not all galaxies are the bright, well-defined islands of stars we might imagine. In recent years, astronomers have discovered a class of galaxies so faint and spread out that they've been called ultra, diffuse galaxies, ghostly apparitions barely visible against the night sky. These galaxies can be as large in extent as the Milky Way, yet have only a tiny fraction of the stars. Picture a galaxy with the diameter of a giant spiral, but the total luminosity of a dwarf galaxy, effectively a huge puff of stars so sparse that if you lived inside it, you might not realize you were in a galaxy at all, because the stars would be so few and far between. One example that made headlines is Dragonfly 44, a faint galaxy in the Coma cluster. When first studied, Dragonfly 44 appeared to have about the mass of the Milky Way, but only about 1% of the number of stars, implying it was 99% dark matter by mass. It was dubbed a failed galaxy, or a dark matter galaxy, as if it started forming like a normal large galaxy, but somehow failed to produce many stars. Dragonfly 44 also sports an unusually rich system of globular clusters for its luminosity, supporting the idea that it once had the potential to be a big, star-filled galaxy, but didn't follow through. This and other UDGs beg the question, how do you get a galaxy that big with so few stars? There are several ideas. One is that these UDGs formed in high-spin halos. The gas was spread out over a larger area and thus never condensed into the dense concentrations needed for prolific star formation, resulting in an oversized but dim galaxy. Another idea is tidal heating. Perhaps they were once normal galaxies that got puffed up by gravitational tides in a cluster environment, stretching them out and thinning their star distribution. Some might be failed giant galaxies. Their dark matter halo and initial gas were like that of a large galaxy, but something prevented normal star formation. What remained is a dim shadow of a galaxy, mostly dark matter, holding a thin sprinkling of stars. On the other extreme of the spectrum are reports of galaxies that seem to have very little dark matter at all. In 2018, astronomers announced the discovery of a galaxy named NGC 1052, DF2, that defied expectations. This diffuse galaxy, about the size of a dwarf, appeared to have so few stars that one would expect it to be dominated by dark matter, yet the velocities of those stars were so low that they implied the galaxy's mass was nearly all accounted for by the visible stars. In other words, it seemed to lack the unseen mass that every other galaxy its size needed. A year later, a second galaxy in the same group, DF4, was found with similarly anomalous properties. These no-dark matter galaxies caused a flurry of both excitement and skepticism. If true, they would be the first galaxies discovered that contradict the rule that galaxies form within dark matter halos. Could it be that dark matter can be stripped entirely from a galaxy, leaving behind a wraith of stars? Or might there be an alternative explanation? One possibility is that these galaxies did form in normal dark matter halos, but later experienced a gravitational interaction that sheared away most of their dark matter. For example, if DF2 and DF4 passed very close to a much larger galaxy, the tidal forces could have pulled out a large fraction of their dark matter and outer stars, leaving behind an inner core of stars with little surrounding halo. Another clue, DF2 and DF4 both have unusual populations of globular clusters, fewer in number, but unusually luminous for the galaxy's size. This might hint that something about their formation was atypical. Some later studies argued the distance to these galaxies might have been overestimated initially. If they are a bit closer than first thought, then they have fewer stars, and the original no dark matter conclusion may soften. The jury is still out, but most scientists suspect these galaxies aren't truly dark. Matter-free, but rather odd products of interactions. Important nonetheless, because they show how far interactions can go in reshaping a galaxy. When we say dark galaxies, we could also mean the purely hypothetical objects made almost entirely of dark matter, with virtually no stars at all. Our cosmological models predict that there should be many small dark matter halos that failed to form stars. These would be completely invisible to us, except through gravitational effects. Detecting one directly is extremely challenging. How do you see an object that emits no light? One strategy is via 21 pound-centimeter radio surveys of hydrogen gas. Astronomers have searched for isolated clouds of hydrogen, with motions indicating they are held together by some mass, yet with no visible stars, essentially a dark galaxy candidate. A few candidates have been reported. One famous one, discovered in the Virgo cluster, was a large cloud of hydrogen that some thought might be a dark galaxy. However, skepticism remains, as it's hard to distinguish a truly dark galaxy from tidal debris. So far, no incontrovertible 100% dark galaxy has been confirmed. But the hunt itself is telling. If we found even one, it would confirm that starless galaxies can exist and would be a direct piece of evidence for the prevalence of dark matter halos without baryons. What do these ghostly galaxies tell us? For one, they underscore the complex interplay of matter in galaxies. We have galaxies like ultra, diffuse ones that are heavily dominated by dark matter, and perhaps others that are so dominated by normal matter that they barely show dark matter's presence. This diversity challenges our understanding of galaxy formation. Our theories have to accommodate both ends of this spectrum. They also serve as natural experiments. For example, a galaxy lacking dark matter would be a huge test for alternative theories of gravity, which predict you can't have one without the other. Conversely, galaxies with extreme dark matter dominance test our models of star formation efficiency. Why did they form so few stars relative to their dark mass? Ultra, diffuse galaxies also likely hint at the role of environment. The fact that many UDGs are found in clusters suggests that environment, e.g. interactions with other galaxies or the cluster's tidal field, might be responsible for their puffed-up nature. They might be the blown out remains of formerly normal galaxies that got their gas removed early and their structures distended. In less dense environments, such fragile, puffy galaxies might not survive. The cluster both creates them and, ironically, helps preserve them by confining them in its gravitational embrace. As we continue exploring these extreme galaxies, we sharpen our understanding of the thresholds of galaxy formation. We learn what it takes for a dark matter halo to actually light up with stars, and what circumstances can prevent it. We see how galaxies can be stripped to the bone by interactions, and how nature can produce objects that challenge the very definition of a galaxy. After all,
A galaxy has traditionally been defined as a gravitationally bound collection of stars. But what do we call a gravitationally bound collection of mostly dark matter and almost no stars? Or conversely, a tenuous collection of stars that seems to have shed its dark matter? These edge cases blur the lines, forcing us to refine our definitions. The mysteries of ultra, diffuse and dark galaxies remind us that there is still much to learn about the invisible scaffolding of the cosmos. With new telescopes and surveys, we are now better equipped to find more of these phantom galaxies and unravel their stories. Each such discovery is like finding an unexpected creature in the cosmic wilderness, challenging what we thought galaxies could or couldn't be. After exploring the extremes of galactic forms, from the magnificent to the barely there, we return now to the grand perspective of the universe. We've spoken of countless galaxies, but how many can we actually see? How far does our vision reach? Next, we'll discuss the observable universe, how deep our telescopes peer into the cosmic past, how many galaxies likely populate our universe, and what lies at the edge of our sight. The observable universe, counting galaxies and reaching back in time. Our journey through the cosmos has taken us from our own Milky Way to the farthest reaches of galactic existence. One naturally wonders, how many galaxies are there? And how far can we see into the depths of space and time? The truth is both humbling and exhilarating. When the Hubble Space Telescope pointed its lens at what seemed to be an empty patch of sky in 1995 for 10 days, the resulting image, the Hubble Deep Field, revealed thousands of galaxies of all shapes and colors packed into that tiny speck of sky. This was followed by the Hubble Ultra Deep Field in 2004, an even longer exposure that unveiled nearly 10,000 galaxies in an area of the sky only a fraction of the moon's apparent size. Every swirl, blob, and smear in those deep images was an entire galaxy, some as they were over 13 billion years ago. Extrapolating these results to the whole sky suggested that the observable universe contains on the order of hundreds of billions of galaxies. For a long time, a common estimate was around 200 billion galaxies in the observable universe. But even that might be an underestimate. In 2016, using data from new surveys and some clever modeling, astronomers proposed that there could be as many as 1-2 trillion galaxies in the observable universe. Many of those would be very small, faint galaxies, the kind that current telescopes can't easily see, especially those that existed in the early epochs of the universe. It's sobering to realize that every time you look at a clear night sky, the few thousand stars you see belong to our Milky Way. Yet overhead, invisible to our eyes, are billions upon billions of other galaxies, each with its own stars, planets, and perhaps life, scattered across the universe. The phrase observable universe is key. It refers to the portion of the universe from which light has had time to reach us since the Big Bang. Because the universe is about 13.8 billion years old and space has been expanding, the current radius of the observable universe is about 46 billion light years. That encompasses an immense volume. Think of a sphere centered on Earth that includes all galaxies, whose light has traveled 13.8 billion years or less to get here. Galaxies beyond that horizon are simply too far for their light to have ever reached Earth in the age of the universe. They may exist, but we cannot see them, and they cannot see us. How far have we seen? With the Hubble Space Telescope, we detected galaxies at around 13.3 billion years back time. One example was a galaxy nicknamed GN-Z11, observed in Hubble's deep surveys at a redshift of about 11. That was a record for some years. Now, thanks to the James Webb Space Telescope, we've pushed the frontier even closer to the dawn of galaxies. In 2022-2023, JWST identified galaxies with tentative redshifts of 13, 14, even up to around 16, if confirmed.
Those correspond to times just 250–300 million years after the Big Bang. We are likely seeing the flicker of some of the first generations of galaxies that formed in the universe. These farthest galaxies are tiny and primordial, looking often irregular agglomerations of stars, blazing with the light of massive newborn stars, but relatively low in mass. They lack the heavier elements that subsequent generations of stars would build up. Observing them is like peering back in time to watch the universe's infancy, the cosmic dawn, when the first galaxies and quasars burst into light and began reionizing the fog of hydrogen that filled space after the Big Bang. Each new leap in telescope power effectively extends our time machine further. JWST is now letting us study in detail the era when the very first galaxies took shape. So, how many of those galaxies can we actually see? In practice, even with our best telescopes, we cannot see all the hundreds of billions of galaxies out there. Many are too faint or too redshifted. But we can see an astonishing variety. From the grand spirals a few million light years away, to ancient red ellipticals in distant clusters billions of light years away, to tiny blue specks that are infant galaxies in the early universe. As telescopes improve, our observable catalogue of galaxies grows. The upcoming Vera C. Rubin Observatory will map billions of galaxies across the sky, though mostly relatively nearer ones. Space telescopes like JWST and the planned Nancy Grace Roman Space Telescope will focus on finding and analyzing the faint, distant ones. What does this reveal about the universe's timeline? By surveying galaxies at different distances, we can trace the evolution of galaxies over cosmic time. We see that in the early universe, galaxies were generally smaller, more irregular, and forming stars at a furious rate. Many were clumping together and merging. As time went on, small galaxies combined into larger ones, star formation peaked, and then gradually declined. Galaxies in the more recent universe often appear larger, more mature, with well-defined structures like spiral disks or big diffuse ellipticals, and many have slowed their star formation. By looking as far back as JWST allows, we're trying to witness the moment when the very first stars and galaxies ended the cosmic dark ages. We also glean the universe's timeline from the most distant light of all, the cosmic microwave background. This is not a galaxy, but the faint remnant glow of the Big Bang itself, released about 380,000 years after the Big Bang, when the hot plasma cooled enough for atoms to form and light to travel freely. The CMB comes to us from every direction, a nearly uniform background with tiny fluctuations that encode the seeds of future galaxies and clusters. It represents the absolute limit of what we can see via electromagnetic radiation. Beyond that, the universe was opaque. It's like a foggy wall at the edge of our vision. We cannot see through the CMB with light. It's the backdrop of the observable universe. Thus, our observations currently span from the present day all the way back to those first few 100 million years, when the earliest galaxies and black holes were turning on, and finally to the CMB wall at 13.8 billion years ago. Each big telescope and survey has effectively peeled back another layer of the universe's history. Our picture of the cosmos's timeline has grown rich. We have seen the universe as a baby, as a rambunctious toddler, as a vigorous youth, and in its middle age. As for how many galaxies exist in total, the number is truly mind-boggling and might ultimately be unanswerable if the universe is infinite. But in the observable volume we inhabit, current best estimates suggest on the order of 1 trillion galaxies. It's a number so large it loses meaning. Suffice it to say, there are more galaxies in the observable universe than there are stars in any individual galaxy. Looking up at a dark sky, one might feel that the universe is mostly empty darkness sprinkled with stars. But thanks to our instruments, we know the opposite is true. The darkness is filled with the light of galaxies. stretching to the edge of what is knowable. Standing here, on a small planet within the Milky Way, we have managed to gauge the universe's extent and populate it with galaxies by the billions. This achievement of human curiosity sets the stage for our final reflections on what it means to live in a universe so vast and full of galaxies, to be made of the stuff of stars, and to contemplate it all from our tiny corner of the cosmic ocean. Eyes on the cosmos, telescopes that revolutionized our view. Our understanding of galaxies has expanded hand in hand with the advancement of our telescopes, our eyes on the universe. Even before the space age, giant ground-based telescopes pushed our galactic knowledge. The 100-inch Hooker telescope on Mount Wilson in the 1920s allowed Edwin Hubble to measure galaxies' distances and the expansion of the universe. The 200-inch Hale telescope at Palomar was the world's largest for decades. It revealed exquisite details in galaxies and allowed astronomers in 1963 to identify the first quasar, realizing it was an unbelievably distant powerhouse. Each leap in technology has brought a leap in knowledge. In particular, a few key instruments and missions have transformed our view of galaxies in ways earlier astronomers could only dream of. The Hubble Space Telescope, launched in 1990, has been often called one of the most productive scientific instruments ever built. Above the blurring effect of Earth's atmosphere, Hubble has provided crystal, clear images of galaxies near and far. It showed us spiral galaxies in unprecedented detail, glittering arms and delicate dust lanes, and peered into the cores of ellipticals to find evidence of central black holes. Hubble's most famous contribution might be its deep field observations. By staring at empty patches of sky for days, HST captured the Hubble Deep Field and Ultra Deep Field, revealing a rich backdrop of galaxies stretching to the horizon of the universe. These images fundamentally changed our perception. Every tiny patch of sky, if you look long enough, is teeming with galaxies. Hubble also provided distance measurements via Cepheid variables and supernovae that helped nail down the scale of the universe and the rate of its expansion. Its crisp images of galaxy collisions, gravitational lensing arcs, and proto-galactic fragments have filled textbooks and our collective imagination. If Hubble opened a clear window in visible light, the James Webb Space Telescope, launched at the end of 2021, has opened a new window into the infrared universe. Galaxies emit light across the spectrum, and by looking in the infrared JWST, can see through dust clouds that obscure stellar nurseries and detect the faint glow of extremely distant galaxies whose light has been stretched into the infrared by the expanding universe. In its first years of operation, JWST has already identified some of the earliest galaxies ever observed, spotted rich organic chemistry in galaxy gas clouds, and produced stunningly detailed images of galaxies like never before. JWST's ultra-sensitive infrared vision is giving us a direct look at the cosmic dawn, complementing Hubble's view of the later universe. Together, Hubble and Webb act like time machines, Hubble mapping the middle epochs and Webb pushing toward the beginning. Beyond these two famous space telescopes, there have been and are many other missions that significantly advanced galactic astronomy. Radio telescopes. In the mid-20th century, radio dishes like those at Jodrell Bank and later the Very Large Array in New Mexico started mapping radio emission from galaxies. They discovered jets and lobes emanating from active galactic nuclei. Radio surveys found quasars before we knew what they were. Bright radio sources with star-like optical counterparts that turned out to be distant AGNs. Today, radio telescopes like ALMA can detect the cold molecular gas in galaxies billions of light years away, revealing where future stars will form and how galaxies acquire fuel. They also measure the rotation of outer gas in galaxies to chart out dark matter distributions. Interferometric radio images of colliding galaxy clusters have even detected the shock waves of cluster mergers and the halo radio glow from cosmic ray electrons in cluster-scale magnetic fields.
X-ray observatories, space-based. X-ray telescopes, such as Chandra and XMM, Newton, have shown us the high-energy side of galaxies. They map the X-ray glow of hot gas in galaxy clusters, providing direct measurements of cluster masses. Chandra's sharp vision revealed how clusters collide. X-ray images of galaxies show the halo of hot plasma that many galaxies, especially ellipticals, sit in, and pinpoint the light from accreting black holes at galactic centers or ultraluminous X-ray binaries sprinkled throughout galaxies. X-ray surveys also discovered mysterious diffuse X-ray backgrounds and contributed to the discovery of intergalactic filaments of warm hot gas connecting clusters. Infrared and UV surveys. Before JWST, we had Spitzer, which, though smaller, detected countless dusty stars, forming galaxies, and helped uncover ultra-luminous infrared galaxies. Spitzer observed high, redshift galaxies in infrared 2, bridging some of the gap until JWST. In the ultraviolet, the Galactic Space Telescope mapped UV emission across the sky, highlighting where in galaxies young massive stars are concentrated. Galac's pictures of spirals showed hazy UV halos of star formation and star streams, and captured starburst activity in dwarfs and interacting galaxies. Ground-based surveys and upcoming telescopes. The Sloan Digital Sky Survey, starting in the 2000s, used a dedicated 2.5-meter telescope to perform an immense imaging and spectroscopic survey of galaxies. SDSS gave us a 3D map of over 1 million galaxies, which led to the discovery of large-scale structures like the cosmic web filaments, and refined our understanding of galaxy demographics. The forthcoming Vera C. Rubin Observatory in Chile will take this further, imaging the entire visible sky to great depth repeatedly and capturing billions of galaxies and their changes over time. The Nancy Grace Roman Space Telescope will conduct wide field surveys at near infrared, providing a Hubble-like clarity, but on areas of sky hundreds of times larger, ideal for finding distant galaxies and mapping dark matter via weak gravitational lensing. And on the ground, the new extremely large telescopes will, later this decade, give astronomers unprecedented power to study faint galaxies and directly image features in galaxies tens of millions of light years away that currently appear as mere smudges. They'll also dissect the light of very distant galaxies into spectra to determine their compositions and internal motions in detail, complementing Webb's work with brute force light, gathering, and sharp resolution. Each of these tools, whether in space or on the ground, has peeled back a layer of the cosmic onion, bringing galaxies into better focus. Our toolkit now spans the full electromagnetic spectrum: radio, microwave, infrared, optical, ultraviolet, X-rays, and gamma rays. By combining all these views, we get a holistic picture of galaxies that was impossible a century ago. It's remarkable to think that barely a lifetime ago, we didn't even know other galaxies existed. Now, with our Hubbles and Webbs and myriad other instruments, we routinely catalogue galaxies, billions of light, years distant, capture images of their shapes, break their light into spectra to gauge their compositions and star formation rates, and even watch as they collide or as their cores light up as quasars. Missions like Hubble and Webb stand as milestones in this ongoing journey, each bringing the universe's galaxies closer to us. As we consider these powerful tools and the discoveries they have enabled, we prepare to leave the domain of scientific observation and enter a more introspective realm. With the data gathered by these instruments, we can now reflect on what it means to live inside a galaxy, to be made of stars, and to find our place in cosmic time.
In the final section, we'll step back from the technical and immerse ourselves in the philosophical and existential implications of knowing that we are part of a universe filled with galaxies. Reflections. Our place among the galaxies. On a warm, clear night, if you find yourself far from city lights, you can see the Milky Way arching overhead, a milky band of light splashed across the sky. That soft glow is the combined shine of billions of distant stars in our home galaxy, seen from within. We live inside a galaxy embedded about 26,000 light years from the Milky Way's center, orbiting with our sun and planets among the spiral arms. For most of human history, we didn't know that we were inside a galaxy, or even what a galaxy was. Now, in the light of all we've learned, think about what that means. It means that when you gaze up at the Milky Way, you are seeing the structure of our galaxy from the inside, the disk of stars and nebulae in which our sun is just one modest member. It means that our sun is one of perhaps 400 billion stars in the Milky Way, and our Milky Way is one of perhaps 1 trillion galaxies in the observable universe. Our Earth is a tiny world circling a garden, variety star, in the outskirts of one galaxy, among uncountable others. This realization can make one feel incredibly small. The scales are almost too vast to hold in the mind. The distance to even the nearest major galaxy, Andromeda, is 2.5 million light years, so far that the light hitting your eye tonight from Andromeda left that galaxy when early human ancestors were just beginning to make stone tools. And yet, consider the flip side. Though we are tiny, we are also a part of this grand universe. We are made of it. The iron in your blood, the calcium in your bones, the oxygen you breathe, those atoms were forged long ago in stars, likely in the Milky Way, during stellar alchemy and violent supernova explosions. We are made of stuff, the products of galactic recycling. Over the history of our galaxy, generations of stars lived and died, each enriching the cosmic clouds with heavier elements, which eventually found their way into the gas that formed our sun, our planet, and ultimately us. In a very literal sense, the galaxy is in our bodies. We are the universe, in a small way, contemplating itself. As one philosopher, scientist mused, we are a way for the universe to know itself. Atoms with curiosity, as someone once said. From our vantage point on Earth, we've managed to decipher the Milky Way's structure, learn the history of galaxies, and even map the large-scale cosmic web. Feats of understanding accomplished by a clever species of primate using telescopes and mathematics. It's astonishing. The universe became aware of itself through us. We, tiny and fragile, can mentally span billions of light, years and billions of years, reconstructing events and structures we will never physically touch. When we look at a picture of a distant galaxy, we're seeing a piece of the universe's autobiography, a chapter from a time and place utterly remote, yet connected to us through the simple act of a photon of light traveling across space and landing in a telescope mirror. To live inside a galaxy is to be both extremely insignificant and extremely special. Insignificant because the galaxy does not notice us. The Milky Way would be essentially unchanged if our solar system vanished tomorrow. We occupy no central role. The universe is not arranged with us in mind. But special because despite that, we have the unique gift of consciousness to appreciate the cosmos. The stars in the Milky Way burn on obliviously, yet here on a rocky planet around one star, the atoms assembled into beings that can admire the beauty of a spiral galaxy, that can feel awe at the sight of the Milky Way's shimmering band, that can wonder about the possibility of other minds in those other galaxies doing the same. We have, in a sense, imbued the galaxy with meaning simply by being here to observe it. Galactic timescales stretch far beyond human lifetimes. Our solar system orbits the galaxy every 230 million years, making one galactic year. A human life is a mere instant by that clock. In fact, when dinosaurs roamed the Earth, it was roughly one galactic year ago.
In one sense, that might make our lives feel vanishingly short, but it also means that life on Earth is tied into the dynamic life of galaxies. Civilizations might rise and fall while galaxies perform their slow gravitational dance. Perhaps in some distant future, beings will witness the night sky dramatically change as the Milky Way merges with Andromeda. None of us will see that, but knowing it will happen connects us to the far future and to the long narrative of our galaxy. When confronting these immensities, it's natural to ask, what do galaxies mean for us? They can make our everyday concerns feel small, the petty squabbles, the borders we draw on our tiny planet. Viewed against the cosmic backdrop, such things seem trivial. Many astronauts, after seeing Earth from space against the void, report a profound overview effect, a shift in perspective, recognizing the unity and fragility of life on our pale blue dot. A similar effect comes from the cosmic perspective, recognizing that all humanity shares one tiny home galaxy, that we have far more in common with each other than any difference, and that our true tribe is as large as the Earth, perhaps even as large as the Milky Way. We are all voyagers together through the galaxy. There is also a deep comfort and inspiration in this perspective. The atoms that make us have endured across billions of years and multiple galaxies' journeys. They will persist long after we are gone, possibly incorporated into new living beings or new worlds when our sun's time is over. We are part of something continuous and far bigger than ourselves. The light we make, radio waves carrying our broadcasts, for instance, is even now leaving the Milky Way and traveling into intergalactic space. In that sense, a piece of us will touch other galaxies, albeit faintly. Knowing about galaxies also invites a profound humility. We inhabit a universe where the dramatic and the sublime are commonplace. Galaxies crash together, black holes light up as quasars, stars are born and die in colorful nebulae, entire clusters of galaxies dance in gravity's grip. Against such a backdrop, the significance we assign to our own achievements or struggles finds a healthy perspective. But rather than make us feel despair at our smallness, this awareness can instill a sense of gratitude and wonder. Out of all the possibilities, we have the privilege to witness and understand a slice of the universe's story. Finally, consider that for most of history, the galaxies were unknown to us. Only in the last century have we recognized what the spiral nebulae truly are. In that short time, essentially a couple of human lifetimes, we've gone from not even knowing other galaxies exist to mapping the cosmos and decoding the light from the dawn of time. This rapid progress shows something powerful. Our desire to learn is as expansive as the universe itself. We are a curious, bold species, unafraid to ask big questions. What is that hazy band in the sky? What are those faint smudges in the telescope? How did we come to be? And remarkably, we've been able to answer many of them. As we conclude the story of galaxies, we find that it is deeply intertwined with our own story. Galaxies are not just distant objects. In a very real way, they are our extended homes. The Milky Way gave birth to the Sun and Earth. Galaxies provided the raw materials for life and the stage for every cosmic event that led to our existence. When we marvel at the galaxies, we are in a sense marveling at our origins. And we are fortunate to live at a time when we can see them, eons from now. The expansion of the universe will carry many galaxies beyond our observable reach, potentially leaving future civilizations more isolated. We, however, inhabit a cosmic epoch rich with galaxies to observe and learn from. So, the next time you find yourself under a truly dark sky, allow yourself a moment of communion with the Milky Way. Think of the myriad stars you see and know that you are connected to them, that you are made of their fire, that your existence is tied to their past. Think of the countless galaxies beyond, each with its own wonders and perhaps its own watchers. Feel the swell of awe that comes from realizing you are part of a cosmos so vast and magnificent. In that feeling lies something profoundly human and profoundly beautiful, a sense of belonging to the universe itself.